been to the lab since March, but luckily I've been able to, and I'll show you this today, I've been able to use the kinds of open source offerings we have, Qiskit, Qiskit Pulse, to be able to do experiments and all kinds of things, you know, over the internet instead of in person. So it's great.
Very good, looking forward. Yes, and you will obviously get a chance to reintroduce yourself once you begin your talk for folks who will show up by the time. So let's go with Andre next.
All right. I used to live in New York, just like Nick, for 15 years, but moved down to Miami Beach, like many New Yorkers, about a year ago. So I'm looking at the beach right here. And
Nice.
promised to only take 3 hours of my time, and then I'll be going to the beach with my picture of margarita. I'm originally from Germany. I've lived in the US for 20 years. My background is a split between a dozen years of management consultancy and then a dozen years as an entrepreneur, where I founded 5 startups, then became a mentor, investor, and so forth over the last 3.5, 4 years exclusively in quantum.
Great, thank you. And again, we're looking forward to your talk. I appreciate you joining us early. You know, I hope it's of interest, but obviously, you know, we're online, so everybody is present from around the world. Now, Michael Seder.
Yes.
Hi, Michael. Tell us a little bit about yourself and what are you working on?
Well, my background is electrical engineering. I'm interested in all aspects of quantum computing and quantum physics. And I'm located in on the Upper East Side of Manhattan, New York City.
Nice. You know, guys, if you like, please share with us what you want to get out of these meetings, and maybe what you want to do at these meetings, if you want to present or if you want to find collaborators. All right, if you're looking for reviewers, if you're looking for ideas, so feel free to add that, because it's essentially the community meeting. We can best use it basically as best we can, and it's really up to us to have fun and basically make the most of it, right? So feel free to add something. So maybe Michael, you'll share like what are you looking for in these meetings? What what's most interesting to you?
Well, I spent most of my career in the computer industry, so I'm just interested in learning new aspects of computing, and I see quantum computing as the future of computing.
Cool. Yeah, I think a lot of us are here for the same reason. So, sounds good. Thank you, Michael. Taha Jaffer.
Hi, folks. Can you see me?
Yes, very well.
Okay.
And we hear you too.
Yeah, thank you very much. So I'm in Toronto, Canada. I work for Scotiabank, and I run one of the large AI ML labs that we have here. And part of our mandate is on the quantum computing side in terms of bringing value to the bank via quantum computing in the near term. And so what I'm looking for from this meeting is not just ideas and collaborators, but I'm also looking to make new friends, as well as just to learn more about what's on the cutting edge and what's happening. We have quite a few partners in and around the Toronto area that are in the quantum computing space. So, we're trying to find ways to make this a reality instead of being something that's 5 to 10 years down the road. So at the bank, we're kind of the pointy end of the stick. My background is in the hedge fund industry. I'm not actually a data scientist. I'm a quantitative portfolio manager. So a lot of the things that the quantum computing side can give me, I think, is an advantage. But on top of all of that, I have a background in electrical computer engineering, as well as physics and finance and math. So this is all really right up my alley in terms of the kinds of interests I have, not only about what's available today, but what's there in the future. And so Joan was very kind enough to connect me into this today. So this is my first meeting, and I'm just looking to learn more.
Thank you, Taha. That's really great to hear from a fellow co-organizer. It may seem easy from the outside. It's a lot of work. From the inside, physical or virtual. So, and Toronto, we in the Bay Area have a lot of links with Toronto, obviously, Waterloo folks, work all around the tech industry, and yeah, I think there is a strong community. So my former CTO actually just moved back to Toronto, where he was from, right? Since Bay Area is all virtual now. So great connections. Thank you. Let's see. So Alex, you're next. Alex Kissinger.
Hi, I'm Alex Kissinger. I'm an associate professor at Oxford University in the Department of Computer Science. I recently joined the quantum group there in computer science, which has for a while been a more theoretical kind of quantum foundations group. But something that I'm getting started there is a new quantum software activity there. So starting from next month, I'll be leading a team there of about six, seven people, mostly PhD students and some postdocs, thinking about things like quantum compilation, quantum circuit optimization, and really doing things which are kind of geared toward the hardware that's becoming available today. So something that's quite interesting for me to be in a meeting like this is to meet some people also outside of academia and industry who are working on these kinds of things, to find some new collaborations and also some new ideas about joint projects maybe that the students or the teams could do. I also gave a talk in the first of these meetings, so that's how I found out about this, yeah, I'm glad to be here. So,
thank you, Alex. Yes, and if you folks want to review the talks, everything goes to our YouTube channel, which is found at the easyurlfunction.tv. So this is the YouTube channel where we publish all the meetup conference talks we produce in the Bay Area, and so there is actually more than 1,000 talks. I think about 300 sponsored by IBM from IBM AI conferences. But a lot of it is basically community content from big data, software engineering, data pipeline. So, I think if you're into computing and different aspects, I think you'll find kind of a lot of cutting edge content from all the Bay Area kind of usual suspects, big and small, right? So this is all going there. Obviously, it's, Creative Commons, free with attribution, embedded, you can share it, right? It's a really educational resource. So yeah, and Alex was, I think the pioneer of this, and we met him through IBM. So I'm really happy, how this worked out. And in terms of disrupting the academic routine, I think we're all for it, because what we find in the Bay Area is that kind of if we disrupt the kind of traditional rituals of something, fun happens, not necessarily good for but something interesting, right? And so I think what I found when I went to a bunch of quantum talks at Berkeley when the world still was open, and they were hiring, I think they're hiring for 2 positions, right? And that's between electrical engineering and physics and computer science, right? Like is in a lot of schools, right? They really, I think, they want to step up and they want to feel the faculty. So, I went to these faculty talks, right, where like the young scientists come in and they want to basically put a stake in the ground. And so what's interesting to me, I think that we're kind of on the verge of change, because a lot of these young scientists are coming from this effectively the environment, lots of collaborations online, a lot of startups are kind of like lurking around, or like the idea of industry has changed, right? When I went to, grad school, more than a decade ago, I think kind of the real world was the anathema, right? Real world will contaminate your science. But I think in computer science, especially, it is now almost part of the course, right? And so I think it's interesting to me that I think quantum, because it comes from physics, I think there is a little bit more conservatism in academia, but obviously it's changing as it's productionizing. So that's why, the idea of these conversations, we want to really diversify them. We want to bring in folks, not necessarily from pure academic background. We want to bring folks from industrial R&D and folks like Andre, who can tell us, right, where the money is going, because in Silicon Valley we find that the money is sometimes kind of a contaminant in other cases a catalyzer, right? Because a lot of smart people are thinking where the field is going. They have this vast networks and they're talking to each other, right? And it's like a jungle telegraph, and they're kind of generating a lot of knowledge filter and seeing what works, what doesn't, applying this kind of pragmatic mindset. And so in that sense, money is a very interesting barometer, right? So we really kind of...
Actually, if I can get 60 seconds, I would actually love to ask our audience a quick question. How many quantum startups do you guys think there is currently in the world? If you look, if you think about it, and across hardware, software, quantum sensing, encryption, shout out a couple numbers if you don't mind. How many startups?
We'll put it in the chat. You guys can put it in the chat, and I can read them up too.
Perfect. And so same question: how much money do you all think has been invested this year so far, globally, private capital, angels, venture capital, private equity, to the closest 10 million? I'd love to hear your thoughts. That way, maybe I can prepare specifically to that a little bit.
So meanwhile, I'm going to be reading numbers, Andre. So we have 200, 320, and we have two numbers of 1,000. So now we have a range from, you know, a few hundreds to a few thousand to 1,000. In terms of money, yeah, another 100 startups. Somebody gave a very specific number, 314 companies. Maybe it's a pie, I guess, times 100 around it. Then we have 100 million and 2 billion in terms of capital estimates.
Interesting, thank you. So
let's see. And yeah, 1,000 startups gets really a lot of votes. So tell us, are we vastly wrong? Are we like in the ballpark?
You're in the ballpark. All the guesses, I think we got the two tail ends.
Interesting. I guess we need to come to your talk to learn the exact numbers.
Absolutely, I'll have them.
Sounds good. Sounds good. Cool. So sorry, I took a little bit of a detour with Alex because I think he hit a lot of notes, which I kind of wanted to introduce as a theme. And we have our audience increasing. So let's spend a few more minutes. We have Augusta Kilbowitz.
Oh, hi. Yeah, hi. I'm currently located at Buenos Aires, Argentina. Yeah, I joined the last meeting. I was working at JPMC, and now I left the company, but I really enjoy the talk, so I will plan to continue coming here. I have a background in physics. I did a master here in Buenos Aires, and now pursue a more financial industry program career. But I always loved the quantum, and now that it's emerging and more accessible to everybody, the part of quantum and computing, it's like merging all my interests. So I'm trying to learn a little bit. That's almost everything for me.
Great, thank you, Augusto. This is awesome. I love Buenos Aires, and you know, it's a great city and convenient time zone, right, for the US as well. The funny thing of JPMC, I don't know if you're in touch with your colleagues. It was interesting because, you know, we had a huge number of folks joining from JPMC at the previous meeting, and right, and Konstantin is an amazing leader. We know him for a long time, but I didn't expect that, you know, he will bring such a vast group of colleagues. So which was really great and kind of indicative that industry is interested. However, when they all registered on Zoom and we sent them an email about this one, they all got filtered by Symantec because they filter all the external emails. So this is, you know, another interesting feature, right? How the industry sometimes, like all this collaboration, because they basically filtered all of our emails. I don't know, who knows? I emailed Konstantin privately to tell him to share, right? Ask him to invite others. But this is an example of challenges we see, because as a software engineer, I knew that banks never use, for instance, Java jars. Like they pick them apart and they look at them. Like you cannot just download stuff into a bank, right? Like security will like maroon you for a week to inspect anything. And so this is an example how you know, we see different groups, right, like moving at different speeds. So, but this is great. Like now you're out, so you can hear, like we can use you as a conduit maybe to like to relay secret messages back to JPMC. Welcome. Daniel Mills is our next member. Daniel.
Hello, good to meet you all. Yeah, so I'm currently in London, but I work for Cambridge Quantum Computing. So yeah, we do a lot of things. So we make compilers, and we have some research in quantum chemistry and security. So I work for the compiler team, but I think these days a lot about error mitigation and things like this. So approaches to making improvements in noise levels through other means besides direct error correction. Yeah, and I'm just excited to meet with everybody, quite a diverse set of specialities here. So I'm keen to discuss with you all what you're up to.
Great, thank you, Daniel. And we got your email, right? We sent a request for presentations, and Daniel sent a great one. And I should tell now, it's very good that you shared, you know, your focus in this context, because we're planning for September. We already have a submission on error correction. I think it's a very important topic. So maybe, you know, if you want to co-present, right? Like we usually do 2 talks. So that may be a folk meeting on that specific field, because I think it's super crucial, right, for the whole area. So I'll follow up for sure. And obviously, you know, the proposal is great. We basically, you know, very accommodating. And so we just want to hear from as many people as possible from different geographies and different, you know, like industry, academia, startups, and investments, right? All kind of fields related. So please, you know, send us your ideas. It's just a question of time, right? Because we're meeting monthly and we're trying to do 2 talks. But, you know, we may do like special meetings in between. So just, you know, if you want to speak, we probably will find a way to do it. And obviously we'll have lightning talks after this if folks still kind of paying attention. Thank you, Daniel. Jamie Gill.
Hey everybody, I am out of Wisconsin, and I've been catching as many of these type of talks as I can. So excited to hear from Andre again, and hear from Nick as well. Nick actually showed me the first quantum computer I ever saw when I was in CES. He was kind of answering questions for IBM earlier in the year in January. So yeah, just really good group, Lexi. So just looking forward to the talks today.
Thank you, Jamie. Yeah, you know, I started recognizing the regulars, so you know it's good. It's good to see you again. And again, like the order is weird. If I read somebody twice, please, you know, don't take an offense. Amir Ibrahimi.
Hey there.
Amir.
Yeah.
Hey.
Yeah, it's good to see some familiar faces here. Alex, I certainly enjoyed PyZX, so thank you for your contributions to that. And yeah, I work for Unity Technologies in our machine learning and deep learning group on the inference side. And just my main goal is to bootstrap until I'm doing active research in the field.
Very cool, very cool. And Unity obviously is, you know, a good partner. So awesome to see this overlap of industries. Now, John Stanton.
Hi, Alex. Welcome. Thanks for having me again. I've been on a couple of these sessions. I'm from Canada, so we're here, you know, with the moose and the bears, and not in Silicon Valley. So, in your honor, I'm drinking coffee from San Francisco Cup today. So, on it. Anyway, I do work with IBM here in Canada, almost 45 years in a number of different areas, but lately in the financial services industry, and specifically do work with Scotiabank, so with Taha and some of his team. And what we're really interested in was some of the information shared by JPMC and some of the others about areas where they're working. So not just noise reduction, but also derivative analysis, portfolio optimization, some of the other areas where people are starting to see some positive work as they move forward on this compared to standard state. So just interested in general on what others are doing. So thanks again for arranging JPMC last time. They were very good. So looking for a really interesting chat today with the different speakers.
Thank you, John. Yeah, appreciate it. And I raise you a glass of Verve, which is Santa Cruz coffee, you know, which is also a great local coffee, highly recommended. Thank you, thank you. It's a good way to start the day. I know you guys a little bit ahead of us, and yeah, that's. I mean, to me, it's super interesting that so many financial folks are in this, right? Obviously, the industry, like technologies, years away probably from direct impact, but I think banks are the most pragmatic and frugal companies, and so if they're doing it, I guess it certainly is of value, right? So so this is interesting to us again, right? Because you guys are seeing something, and you obviously placing these bets and resources for a reason. So it's really good to have you guys here and have you share it, right, to see how this is going. So welcome. Now let's see, Terrell France.
I'm a professor at Harrisburg University in central Pennsylvania in the US. And I get paid by the CIA actually to follow Jamie and Amir, and occasionally Michael on weekends. In fact, I thought Jamie was in another presentation just 20 minutes ago, but I guess he's here as well. I think there's several Jamies. You know, I'm here. I've seen Nick talk, as well as Andre several times. I always walk away with something new piece of information. So I hope that continues. I'm also here this is my first conversations event. I've seen you on the radar 2 or 3 times before. And so I thought I'd get a feel for that. And that's probably what I'm doing here. Anyway.
Awesome.
I'm new to quantum. I'm new to quantum. I consider myself a freshman, if you will. I've just been digging into the topic maybe 18 months or so.
I think we're all freshmen. I know only a few seniors, and probably I don't know if like anybody has a real PhD in this. Probably some folks do, but like the field is young, right? So welcome and thank you. Terrell was sharing. Terrell has a resource actually, right? Maybe you can put it in the chat for quantum events, which is very thorough and actually covers a lot of things which I didn't hear about. So I think it's a discovery, and he obviously discovered this. So, and I guess, you know, the great thing about scientists, they have the machinery for kind of filtering and absorbing new knowledge, right? And so I think it's great, like a lot of folks in academia can go into this new field. And I guess this is how computer science started. When computers appeared, we know computer scientists were mathematicians, physicists, philosophers, and linguists, right? So in a way, I think we see the second wave of this, where people come together from different disciplines, and scientific apparatus and method and community is very important. So in a way, we're building a collaboration framework for the same kind of new age. So welcome. This is great. Vasily Nechayev.
Hello guys. Yeah, I'm software engineer at Crunchbase, San Francisco. I'm just have physics background and I'm interested in learning about quantum computing. Recently finished the Berkeley course for quantum computing and wanted to see what's happening in the field and know people from this field. Yeah. Thanks.
Great, welcome. And Veselin Georgiev, he's our other, I think, regular member, also from academia. Veselin, hope your connection improved. I think you're on mute.
Yes. Thank you. So I'm also drinking from my cup that's actually associated with my previous position that was in China as a visiting assistant professor there. But then it was 2017 where I realized that quantum is coming to an age, and decided to come back to California. So I'm former kind of a academic career path entrepreneur that is switching to understand entrepreneurship. Last month, I went through the CDL, which is Toronto Quantum Bootcamp, and I really enjoyed it. I highly recommend if you have a chance to attend some of the events. That was fun. From there, actually, I came up with a small team that we went last week through iCorp Berkeley, and now we are waiting for their decisions where they were interested in what we are trying to do to keep going. So I'm trying to build a startup around quantum computing and its applications. Thank you.
Hey, Veselin, where in China were you a prof?
Sichuan University.
Sichuan? Oh, ha.
Yeah.
I was at Beijing Dashui.
And how?
Yeah, I was in. Yeah, I too left China. I think it was about 2 years ago now. So.
Yeah. Well,
interesting
that's
experience.
about the same time, probably. Yeah.
Yeah. I was in Shenzhen.
Well, I love China. I mean, that they have very interesting culture and interesting people.
You know, the funny thing is, I lived in Shenzhen, which is like the electronics capital of the planet, right? And I was in the business school there at Peking University, and I moved back to the United States and pivoted over to quantum, to cybersecurity, IoT stuff, and then quantum. But it was ironic, you know, I literally lived, you know, a few kilometers away from these factories that make all these IoT devices, and I never bought one until I moved to the United States. Now, you know, then I just binged on it. So everything was coming from my neighborhood where, you know, when you live there, it's like you just pass it by. It's like the Statue of Liberty in New York City. You just don't pay attention until you leave. And then all of a sudden, you know, I don't know how much I probably paid, you know, $20 for something I could have bought for 50 cents in Shenzhen.
That's true.
Interesting. All right. So our final member to introduce is Zhiyong Zhang. Welcome, Zhiyong. He's a regular for all quantum conversations.
Hi, everybody. My name is Zhiyong Zhang, and thanks, Alex, for organizing this event. It's very interesting. I have been becoming regular now. It's kind of amazing. It's early in the morning. I'm a quantum chemist and computational chemist, and I work at Stanford Research Computing Center. And my interest is applying quantum algorithm to computational chemistry applications. So that's what I've been trying to do so far. Thank you.
Great. Welcome, Zhiyong, again. All right. So I think we actually went through all the introductions, and
Alexei,
it worked really. Yes.
There's one thing I forgot to mention. If I have maybe just 1 minute to say one more thing. So my soon-to-be PhD student, Leah Ye, has started putting together a lot of open source quantum computing educational resources online, which is something some people here might be interested in, and also runs a Discord server with, I think by now, some 50 or 60 people kind of working through these things and doing reading groups and this sort of stuff. Maybe if I send you the link, you could sort of bounce it back to everybody else over the chat, because I don't think I can broadcast something to everybody on the
yeah, I think there were some instances of Zoom bombing, and we had to kind of restrict how this works. So yeah, please send me the links. What I'm gonna do, I'm actually gonna publish them on the our homepage, quantum.sv, which was originally meant to be Silicon Valley, but obviously now it's, you know, the world, right? Oh yeah, please. That's great. The question is, are these resources used in that, you know, in your work? Because if, you know, one way, you know, to have more fun would be maybe to walk people through them, or have a discussion, or have some kind of hands-on tutorial. So obviously, when folks look at open source, if they use it, they play with it, it's still fresh in their minds, you know, how it works. Like sometimes even installing open source takes time, right? And so I would propose, like, I'd love to have a talk where somebody installs a, you know, open source package, shares what's happening, right? So it doesn't have to be, you know, a slide presentation. Actually, in kind of software engineering startup world, the best presentation is live coding. People just code and like they're in the terminal, they're in a notebook, like you did, right? So like this is kind of this is very engaging, and I think it's for a lot of people. So I would say please consider kind of giving like a live coding talk of some sort, reviewing this or something highlights, right? So we definitely welcome it.
Yeah, maybe I'll see if Leo wants to give a lightning talk at some point in one of these to explain kind of what's out there and how this community she's setting up is working and so on. So well, anyway, the address is fullstackquantumcomputation.tech. I sent that to Alexei.
Okay.
So that'll appear on the website, and maybe it'll appear in the chat if he repastes that, or if one of the hosts does.
If I figure out how to broadcast it, because I think I locked myself into a corner now, and I can only chat with what people one-on-one. So it's really, and the funniest thing about Zoom is like you cannot change. When things are on the way, like it's too late. The boat has sailed, right? The train left the station. So yeah, I'll definitely figure out. I see the link, so I'll share it. By the way,
Alexei, if you go in the shield down there, you may change this capability. If you look at the shields options.
Yeah. Okay. I mean, I'll be playing with this as I go. Yes, I see the shield. That's right. That's good. That's right. Maybe I'll see how I'll change it, and I'll try to repaste it as the talks progress. And by the way, guys, this is thank you, Alex. Obviously, folks have announcements, right? Feel free to make a brief announcement, because we'll have lightning talks. We're kind of sharing more after the main program, but if you have any announcements, feel free to like Alex to mention any of those. Everybody. And we'll do again, we'll have a chance, if you can think of an announcement, we'll probably do a quick round in between the talks. Right, so, and obviously we'll have some time in the end for those who stay. All right, guys, I think that's good. So now I think we're ready to start our first talk. It's by Nick Bronn of IBM, and he will do an overview of quantum hardware, which is obviously the key topic. None of this is possible without hardware, and it's much easier to play with software, and you need obviously to be in a special place. And I think a few companies like IBM can actually do this. So we're very excited to have Nick Bronn from IBM with us to give us an overview of hardware for quantum computing and some topics in that space. Welcome, Nick.
All right. Well, thanks a lot for that introduction, Lexi. Can everyone see the slides?
Yes.
Yep.
And feel free to ask me questions during the talk. Like I'm happy to have a conversation and stop on anywhere before we go on to other things and we get lost again. So as you're giving the background, I suppose I'd give you my background. So I'm an experimental physicist. I did not study quantum computing for my PhD because it was still very rare in 2013 when I graduated for people to be doing that experimentally. It's a bit more common now, but I developed a lot of the same skill sets. In particular, you see right here, this is something called a dilution refrigerator. This is what gets our qubits very cold. I was working with superconductors in my PhD, so a lot of the things that we use for building quantum computers out of superconducting qubits, I was already familiar with. So I came to IBM in 2013, started as a postdoc, converted to a quantum computing expert, and then became a research staff member, which is where I am today. And so today what I'd like to talk to you about is enabling near-term noisy quantum hardware, which is, by what I mean is I'm not going to be talking about error correction at all. This is kind of the state of the art for what we have in today. IBM, we have a lot of these systems deployed that you can access online. Other companies have some as well. And in particular, I want to tell you about a more experimental way of accessing them other than kind of the gate-based circuit model that you know. And it's kind of the more experimental angle that I think improves a lot of capabilities, and I hope to show you why that's important today. So a lot of people go back to this slide where the IBM and MIT hosted the first Physics of Computation conference in 1981. And if you look over to the kind of middle right back, you'll see Richard Feynman. And most people say he invented quantum computing because he wanted a computer that obeyed the laws of quantum mechanics to solve his quantum mechanics problem. That would make it computationally efficient for him. But IBM was already working in this space right now. In fact, the guy, Rolf Landauer, who's in the front, in the middle left, and Charles Bennett, who is actually taking the picture here, they have been thinking about the physics of information for some time before then. In particular, there was a lot of concerns about, say, the thermodynamics of computation, because there's so much energy cost. Is there a finite amount of energy that gets spent? And it turns out for classical irreversible computing there is. It's called the von Neumann limit. Von Neumann Landauer limit. So there's always a finite amount of energy cost due to the erasure of that information. But what a lot of these physicists did, basically, is they thought about, well, what are the physical properties of what I'm storing information in? So a lot of times I'll make an analogy to classical mechanics in order to kind of realize what the difference is for quantum mechanics. So if you think about a classical bit, it's always going to maintain its information in a physical system, such as the on-off of light switch, whether current is flowing or not through a transistor, or whether or what the polarity of tiny magnets inside of your hard disk drive are. One of the features of all these systems are they are very nonlinear, and they have a latching mechanism, which means they'll flip to either the on or the off state. And so their logical states are represented by this yellow dot and as a 0, or this blue dot as a 1. Okay, so how's this different than the quantum mechanics? Well, in quantum systems, physical systems such as the atoms or the spin of an electron, you can store the information 0 or 1 in the quantum state of these kinds of things, such as the ground or excited state of an atom, the up or down spin of an electron, or the oscillations in little superconducting circuits that we use. And if you have information stored in this state, your 0 and 1 states essentially obey Schrodinger's equation. And because it's a linear equation, you can take any superposition of those two solutions and provide another valid solution, which is why we have something called superposition. And it's represented by something we call the block sphere, where we have any point on the surface of the Earth as a valid quantum state, where 0 is the North Pole and 1 is the South Pole. And then any point there is a complex superposition of 0 and 1. So what's interesting about this quantum state is these are all the valid solutions, so these are the way you can encode them. It's different from analog quantum computing because we can also entangle the quantum states with each other, which allows us to go to a much larger Hilbert space for quantum computation. But what's interesting about quantum mechanics is even though we can put the qubits themselves in a definite state as represented by this block sphere, whenever you perform a measurement, you are going to collapse it into the eigen basis of what you're measuring. So for example, if I'm looking at the z-axis, I can only measure a 0 or 1, and the point at which it is on the block sphere will give me the probability in which I measure that. So for example, any point on the equator, after a measurement, y will yield the answer 0 and the answer 1 with 50% probabilities each. So what I'm going to talk about now is going in specifically how do we encode this in superconducting qubits, and how do we control it from there. So let's look at a 5-qubit superconducting quantum processor that was one of the first ones we put online 4 years ago. And if we look in these square pockets, we find the qubits themselves. And the qubits are something that is pretty much just a basic superconducting circuit. It consists of this 90-degree rotated equal sign, which represents a capacitor electrically. And it has this really small part between it called a Josephson junction, which is actually a nonlinear inductor. It's really, really tiny. It consists of a superconductor insulator superconductor sandwich. It's the only nonlinear dissipationless inductive element known. And so essentially when we combine these two elements, we have an LC oscillator, albeit a nonlinear LC oscillator, but that's also important as well. We also have superconducting microwave resonators that connect the qubits together and connect the qubits to the outside world. Now these are more like LC oscillators. They're distributed. They're not lumped like the qubit is. But these are used in conjunction with the qubits themselves to read out the states of the qubits, to interact the qubits with each other. And they also are detuned, so they function as filters at the qubit frequency. So what's the big difference between having a linear LC circuit and a nonlinear one? Well, if I was trying to store quantum information in a harmonic oscillator, what you'd see is that you have equally spaced energy levels, which means when I try to drive between 0 and 1, I will accidentally drive between 1 and 2, 2 and 3, 3 and 4. So I cannot distinguish my 0 and 1 states if I have a LC oscillator. However, if I have an anharmonic oscillator with a nonlinear inductance, then what happens is the energy difference between 0 and 1 is different from that between 1 and 2 and 3, and so on. So by just focusing radiation at the transition frequency between 0 and 1, I can pretend like I have only a 2-level system and I can do computation there. So we also refer to 0 and 1 as the computational basis. Now, for superconducting circuits like these, they operate in the microwave regime. Our superconducting circuits are typically around 5 gigahertz. And if you multiply 5 gigahertz by Boltzmann's constant divided by multiply it by Planck's constant divided by Boltzmann's constant, you'll see that that corresponds to an energy of about 240 millikelvin. So that's substantially less than a single degree Celsius above absolute zero. And it's also a lot less than the superconducting critical temperatures of both aluminum and niobium, which are the superconductors that we use. Those are about 1 Kelvin and 9 Kelvin respectively. So this is the reason why you have that fancy fridge on the first slide, because we have to actually operate these guys at a point of this fridge, which is about 10 to 20 millikelvin, which is about what you can reasonably get buying a commercial dilution refrigerator. So I'm going to tie this back to what we're actually doing mathematically. So I'm going to go back to the Bloch sphere for a second, and I'm just going to tell you that the computational states, you might remember using Dirac notation, which is the physicist's favorite way of telling you something is quantum, just is a shorthand for these column vectors. 0 means the column vector 1, 0. 1 means the column vector 0, 1. They represent any points on the Bloch sphere. Then I have these special matrices called polymatrices that were originally developed in order to describe the physics of spin. And in particular, they provide the axes that you can measure across. So you can measure along the x-axis, the y-axis, and the z-axis. For superconducting qubits, at least of our kinds, we're always measuring across the z-axis, which means we can only measure the 0 and 1 state. And this tells us that the 0 and 1 states are the eigenstates of the system with eigenvalue 1 and -1, respectively. But because they're also projectors along those axes, no, sorry, not projectors, but they also generate rotations around those axes. And that's how we generate the unitary transformations that manipulate the states of our qubits, for example. So what you can do is any normal unit vector in the Bloch sphere given by little n, you want to rotate an angle theta around that, you can generate the unitary with this Rn of theta here just by exponentiating that unit vector with a vector of the polymatrices, for example, and you get this somewhat simpler formula that's actually easier to use for calculation. And so you can see what happens if I just want to generate a simple rotation. Well, if I just want to go around the x-axis, I throw the x polymatrix in there, and I can get out a generation, the unitary that will move my qubit from the 1 state to the, from the 0 state to the 0 plus I1 state, in particular for theta equals minus pi over 2. So this is essentially how all of these qubits, or how all these qubit control things work, is the unitary matrices are doing the operation on the qubits themselves. So how do you actually do that in the lab? Well, like I said before, we're using microwave pulses. So we take a pulse at the we take a microwave pulse at the resonant frequency between the 0 and 1 states of the qubit. That's our carrier frequency, and we generate usually a Gaussian type, something close to a Gaussian, which I'll show you later, pulse that essentially brings the qubit between the 0 and the 1 states and all the superpositions thereof. And so I can use these to do rotations around the x-axis, rotations around the y-axis, or in particular, any rotation in the xy plane of the Bloch sphere. The only difference being the phase of that carrier frequency is what's defining the axis of the axis of rotation in the xy plane. So that's great. So what about z rotations? Well, you can combine x and y rotations to generate z rotations. But if you realize you can actually do z rotations for free, because what happens is if you have a z rotation in the circuit, you can just compile it down and shift the subsequent phases of all the other subsequent circuits. And so what that means is that's something we call a frame change. Essentially, it means that z rotations go away in software. You can compile them down. So they're free. You're not actually doing a physical thing, so there's no error associated with it. And this kind of shows that you get an average single qubit error rate that's lower if you employ these frame changes versus actual pulses. So then that's for single qubit control. Then what's special about quantum computing is entanglement. So let's go to what we do with 2 qubits. And I heard there were some electrical engineers in the audience. And so I always like to go back to this. I have a little bit of an electrical engineering background too. I like to go back to this idea with classical computing is what makes a classical universal computer. And that's the existence of being able to do any Boolean operation. And so you have two different gates that that will realize any classical system, and that is the not and the not or. And essentially you have these truth tables, and if you combine those with ancilla bits, then you can generate any Boolean function that you want to, and you can take electrical engineering classes that tell you how to do that. The situation for quantum computing is very similar. You need a certain number of single qubit rotations, even though I just showed you how to do all of them. But you need a particular 2 qubit operation that generates enough entanglement. And there's actually a few different ones of these. There's something called a control knot, where the first qubit is the control qubit, the second qubit is the target qubit. And what happens is the control, meaning the control qubit, will only flip the target qubit if the control qubit is in the 1 state. So if I'm in the 0 state, 0, 0 goes to 0, 0, 0, 1 goes to 0, 1. But if my control qubit's in the 1 state, then I flip the target qubit. So 1, 0 goes to 1, 1, 1, 1 goes to 1, 0. And you can see how entanglement is generated by just looking at these truth tables, because I can take a superposition of these input states, say 0, 0 plus 1, 0. And then if I do a C naught to it, then I get 0, 0 plus 1, 1, which is a special highly entangled state called a Bell state, which we'll come back to later. But that's not the only 2 qubit gate I could use. I could also use something called a control phase. And all a controlled phase does is it gives you a 180-degree phase, or a -1, when both qubits are in the 1 state. There's another popular one called the I swap, which swaps the state of the 2 qubits. And then if anything is actually done, it gives you an I, or the imaginary number, the square root of -1 in front of it, which corresponds to a 90-degree phase. So this is essentially the mathematics of how you get the universal quantum gate set. What happens in the actual laboratory? Yeah, is there a question?
Yeah, I have a question.
Sure.
What happens if you apply a 2 qubit gate between qubits which are in different classical frames?
Oh, so you mean like by which you mean rotating wave approximation?
I mean, so when you said that the Z phase comes for free,
yeah.
Then say I apply a Z phase gate to qubit 1, and then say I want to do a C naught between qubit 1 and qubit 2.
Yeah.
Can that be done just by bookkeeping, or do I need to do something to sort of bring those into the same frame?
I see what you're saying. They are done by bookkeeping, and I think what I have later will answer your question. Maybe we can address it at that point. But that's advanced. That's a little advanced for this point, but good question.
I have another question. Actually, it's down on me just now, because this is really nice slide summarizing classical computing and quantum computing. And I just realized that it seems to me there is no reason not to have a C naught in a classical computational framework. Isn't that right?
You can have a C naught in a classical way. The problem is and this is actually, you just made an insight that I totally skipped over, but it's very important. Notice that for the classical computers, you have 2 inputs and 1 output. Whereas the quantum computer, you have 2 inputs and 2 outputs. And that's because quantum computing is a reversible theory, or a reversible system of computing, whereas classical computing in this way is not reversible. There are ways you can configure it to make it reversible, and that was kind of a lot of the ideas that Charlie Bennett and Rolf Landauer were kicking around in the 70s and 80s. If you have a reversible computer, then you don't have that von Neumann and Landauer energy cost, for example.
Okay, thanks.
But there are schemes in which you can realize this, but it turns out not to be the same one that we're using.
Yeah.
And then I guess one of the other things is it's interesting because in quantum computing, I didn't touch on this, but you cannot copy arbitrary quantum information because you essentially destroy it by measuring it. So you cannot essentially make a clone of it. However, you can teleport it. It's kind of, they seem like they're opposite things, but they're really, they seem like they'd be similar things, but they're really not. Yeah, so continuing on, so the choice of which one you use here for your 2 qubits is kind of up to your qubit architecture. Even for superconducting qubits, you can realize any one of these. And then other hardware is going to be more conducive to other kinds as well. But for your different kinds of circuits, there's different kinds of engineering choices that you make. And so what I'm going to talk about is what we do at IBM. We do something called the cross-resonance gate. And essentially, it's locally equivalent to a C0. You need some single qubit operations, but essentially it's a ZX operation. And so let me tell you what that means. So a ZX rotation just means I'm going to generate a rotation that's based on the tensor product of the Z and X, just like we did before with the rotations in the block sphere. Now I'm going to take the tensor product, and I'm going to form the rotation that's based on that. So when I stick that ZX in that formula, I get a matrix where you can see that the rotation of the target qubit depends on the state of the controlled qubit, which sounds a lot like what a C0 is, and that's because it is. And if you look in the matrix, the upper left of this part, which corresponds to the subspace in which the control qubit is in the 0 state, you'll see that this is a rotation of the target qubit around the x-axis. And if you look at the lower right block, where you're in the subspace in which the control qubit is in the 1 state, you'll see that this is a negative rotation around the x direction and around the x-axis in the opposite direction. So this essentially just generates this rotation where the rotation of the target depends on the state of the qubit. And I'm going to try and show you a picture to try and make this more sense. So whenever we think about things in physics, we look and see how things are done with one state, we look and see how things are done with another state, and then we know we can take a superposition of any of those, and that's valid as well. So that's kind of how we think about it, like in this way. And what I like to think of is just forget everything about the purple vector right now. So I'm looking at the control qubit in the 0 state. And I'm going to start with the target qubit in the 0 state as well. But what happens when I apply this cross-resonance operation? What will happen is, because the control qubit's in the 0 state, my target qubit's going to rotate to the right in this direction. Okay, so that's cool. Well, now let's forget about this purple qubit in the 0 state and focus on the blue qubit in the 1 state. Okay, now because I'm in the 1 state, I start with the target qubit also in the, starting from the 0 state. We always tend to start from the 0 state. And then I apply the cross-resonance gate. Then what happens in this case is my target qubit rotates to the left, as represented by this blue vector right here. So then, in order to generate entanglement, and this is something incredibly hard to draw, I will prepare this yellow vector, which is the control qubit in an equal superposition of 0 and 1. And when I'm in this yellow vector and I apply the cross-resonance gate, the target qubit starts in the 0 and it rotates in a linear combination both to the left and to the right, which is, kind of impossible to visualize, but this is the kind of the best I can do. But you can see that, like, the superposition of both those states is occurring at the same time. Okay, cool. So what's actually happening in the lab? So one of the reasons that we choose the cross-resonance operation, the ZX is related to C0, so that's very good. But there's a lot of engineering reasons, quantum engineering reasons that we're doing it. The first one of these is that it's an all microwave entangling gate. We do not need any flux pulses, any kind of DC lines to modify or tune any kind of element of this. Everything is fixed, and that's the way we do things at IBM, because in order to get the highest coherence for your qubits, we want to reduce the number of available channels for decoherence. So if you keep everything fixed, that's kind of one of the best ways to do it, we think. So we prefer this gate where you don't need any other tunable elements. Of course, this presents a whole slew of engineering challenges that experimentalists are working on in the lab, and everything I'd be happy to discuss later. But basically, I just want to give you an overview of what this is. Essentially, we have one of these microwave transmission lines. We call it a bus resonator because it couples quantum information between 2 qubits, one on the left and one on the right. The J is just the coupling rate. So there's slightly hybridizing the qubits. So the left one becomes like the right one, and the right one becomes like the left one. So normally, you would control your Q1 with pulses at the frequency of Q1 in blue, and normally you'd control Q2 on its own with pulses at the frequency Q2 applied to Q2 as well. The frequency of Q1 is applied to Q1. So the reason we call this cross-resonance is what we do is we drive the control qubit at the frequency of the target qubit, and we apply it to the control qubit as well. And so what that does is it generates rotations of Q2, but dependent on the state of Q1. And if you're a physicist like me, you feel a lot more comfortable looking at energy level diagrams. So let me just briefly explain what this is. So this is these energies, the energy is on the y-axis here, and I have the control as the first qubit and the target as the second qubit. So if I didn't have any interactions between these, I would have you know, just uncoupled 1, 0, 0, 1, and 1, 1 energy states, where these guys are going to be different from each other because I didn't mention it when I said it, but this Josephson junction, when you fabricate these things, this is just kind of an aluminum oxide. It's just kind of a, you know, amorphous glass that is between the superconductors. So even if you prepare them all identically, because it's an amorphous growth, you're not going to get the identical critical current through these Josephson junctions. So that's going to affect their frequency via natural spread. So what happens is, if they're not interacting, they're on these dotted lines, and as soon as you put this J microwave bus resonator between them, then you've coupled them together, and they're going to repel each other in energy, and so you get this plus and minus, plus or minus J over delta. So this kind of shows you the hybrid way, where J is the strength of the coupling, and delta is the detuning or the frequency difference in which they are at. And for this reason, you get this dependence on the state of the control qubit when you're trying to drive the target qubit, depending on whether it's in the 0 state, you're driving around this one, or the excited state, you're driving around this interaction. So that's the physics point of view. And let me just say, if there's any questions on that, this is probably about as hard as it gets. Okay, so let's see what it looks like in the lab. And in fact, I'm going to show you a little cartoon of what it looks like for measurement pulses. So I've got a computer that's wired to a bunch of microwave instruments that goes into a dilution refrigerator and then back. So these are going to be measurement pulses I'm sending in here. This actually occurs at a different frequency, usually around 7 gigahertz instead of 5 gigahertz. And I can generate these pulses, which just look like sine waves, and send them into the fridge. And so they go down these lines and thermalize really well, and go through filters and stuff, and they come to this. Did it freeze for everyone or just me?
Yeah, it's frozen.
Whoa.
Okay. But the arrow is moving up.
Okay, no, is it going again now? All right, so so it goes down. We've got to thermalize it. It's, there's an art form. And then these resonators will go in and they'll collapse the state of the qubit to the 0, the 1, and they'll get a state-dependent phase shift imparted on those pulses. And so then those pulses return, they're amplified a bunch because they're very small. When they get to that point, they get mixed down to a lower frequency that can be digitized and classified and stuff like that. And I'll kind of show you how this is done, but that's the general measurement process, and that's roughly what the lab looks like. So I talked about these being noisy quantum systems. So what do we mean by noise, and what do we mean by how do we judge the level of noise of these systems? So we're going to tell you about little device level metrics, and we'll get into a little bit more holistic one later, which is something new I've got for you today. So as I told you, they are kind of like analog control on these qubits. So you can imagine when I'm rotating my qubit around the Bloch sphere, I can easily get over rotations and under rotations, such as in here. So if I do a single pi over 2, I'm off by some error epsilon, and whenever I try and get back, I just get 2 more epsilon each time I try and do it. In fact, we use this for calibration. We call this an error amplification sequence because each one of our steps is going to amplify the error, and then we can use that to more finely calibrate our systems. But there's always going to be some amount of control error. The other thing we'd like to do is I'll talk about decoherence in a second, but because there's a finite lifetime of these qubits, we want to try and do these operations as short as possible. The problem is if you make them too short, you get too much spectral content at those higher order energy levels. So you can get leakage into what we call the non-computational bases, which are the ones that are not 0 and 1, but say 2, for example. You can also get measurement errors, and in this area, I showed you what's the IQ plane, and we call these blob plots. This is essentially the complex plane for measurements, and usually we'll get a blob corresponding to 0, a blob corresponding to 1, and a blob corresponding to, I guess, other things. And then you can also see that when you have these blobs, you have to figure out a way to classify them. So here we've just kind of done it stupidly and put a line where everything on the left is 0, and then put another line and split between 1 and 2. But this is always going to be a problem to classify whether you measured a 0 or 1, because even if you had a perfect system, you always have quantum noise of the measurement, and you're always going to have noise of the amplifier. So that's why these blobs get kind of big. Another thing we have is crosstalk, and that's when we are operating on, say, 2 qubits, and it affects the state of another qubit. So, and this is an example from us as well, when we're trying to do cross resonance between 2 qubits, but we have something called a spectator qubit that's sitting around, but it's being manipulated by it. And in fact, what you're seeing here is a shift of the spectator qubit's frequency, and this frequency shift actually induces a Z rotation error on that qubit. So that's also not good. And then, of course, we have the decoherence methods. We have, we call it relaxation T1. So this is kind of the classical one where you prepare the qubit in a state 0, and it's going to relax back to the state 1. And this can happen several ways. In fact, you can have the opposite way. If your qubits are hot, you can have excitation from the 0 state to the 1 state. But the main ways, usually we're concerned with relaxation, and this can be like spontaneous emission due to the electromagnetic environment. So it kind of behaves just like a LC time constant in any electrical microwave circuit. You can also couple to two-level systems, which are, or any other channel. Two-level systems are usually the material defects, dielectric defects that exist on our device. And then there's other superconductor phenomenon that can affect you, things as quasi-particles, which are unpaired Cooper pairs. Cooper pairs flow without resistance, but quasi-particles do not. You can also have vortices, which can have their own resistances, which are little tornadoes of charge that exist in some superconductors. So there's a lot of very interesting physics that's happening in these things that can cause relaxation. And then there's another thing we call decoherence, or T2, which is kind of an overall metric. This is a combination of pure dephasing, which is the moving along the longitude in some uncertain way. And this is typically due to other effects than T1, but the decoherence T2 is caused by a combination of both the dephasing and the relaxation. And this is typically due to fluctuations in energy levels that could be due to thermal broadening or magnetic noise if you have a tunable qubit. Whenever you have a frequency shift, essentially you pick up a Z error, which will give you this dephasing. Whenever you intentionally measure, whether you measure intentionally or not, you're going to collapse the qubit state. So if you're not shielding from noise, you could be unintentionally looking at your qubits while you're trying to operate on them, which will cause decoherence. And then ultimately, it's going to be limited by this T1. And this is kind of I would say the overall metrics. We have lots of different experiments that we go through to like kind of classify these. And so I'm going to talk about one more holistic metric later, but this is kind of it for the physical systems. And so this might be a good time for questions, if anyone. Okay, then I'll just keep going on. All right, so what I want to talk today is Qiskit Pulse. So how do we do all these things that I was just telling you about with Qiskit, which is, well, originally it stood for the Quantum Information Science Toolkit. And so we shortened it to Qiskit, and Qiskit Pulse is part of it. So just give a brief overview of Qiskit. So down here at the very bottom, we have the quantum hardware, which I was just describing to you, all the things we controlled, what we're doing in the lab. And then we have Qiskit as a software that sits on top of it. And so it's an open source software. It's Apache 2.0. It uses Python. It can control non-IBM hardware. It can control simulators. It can control a lot of things. So we try to make it as modular, as extensible as possible, and build tools on top of it. So fundamentally, Terra is kind of the foundation for us to be able to run quantum circuits on our backends, or the hardware that we have in the lab. And we have several of these that are open for everyone, and several of them that are, and then the rest of them, the premium devices are open for our clients. Are all accessible via Qiskit, and then there's other systems that are accessible via Qiskit as well. We have Ignis, which are tools for characterizing and mitigating error. So this is kind of a very popular thing, because mitigating error is, in order to get the best answer out of the quantum computer, you're going to need to figure out how to do a lot of tricks, and error mitigation is one of them I'll talk about. We have AIR, which is special purpose simulators, to try and figure out where my noise source is coming from. I can throw them into some Lindbladian master equation and see if I can predict what's actually going on in the lab, or seeing what kinds of algorithms I can have that might be immune to certain kinds of error. And then Aqua is kind of the libraries of quantum algorithms that you might want to do, like chemistry, AI, finance, things that you can use and not have to be a quantum computing expert in, so that you can start using quantum computers to do whatever you want to do. So an easier way to explore. And these are all very, we try and make this as easy to install. It's hosted on GitHub. You can do just pip install Qiskit. We just had a release 0.20, which I think has a lot of improvements. We have a Slack community. We have an open source textbook. We have, a lot of a YouTube channel featuring, we also have a YouTube channel featuring a lot of talks at the research level to the coding with Qiskit level. But here, basically, I want to talk about Pulse, which is part of Terra, which gives you this level of control. So this is the second paper we put out about Pulse. I think it's just about to be published for real. So this has been established since 2017, but this essentially defines how do you program quantum computers through the how do you program, like if I was in the lab, which I can't be because of COVID, but I can do it from home using Qiskit Pulse, and how would I do that, and how does it compare to what I could do in the lab? And the answer is there's a lot of things I can do with Qiskit Pulse that allows me to do things better. And those can be things such as optimal control, where you use knowledge of the Hamiltonian and maybe machine learning or something like that to reduce the amount of leakage, say outside the non-computational basis, in order to get faster gates. This is one thing that's done. Error mitigation is something I'll talk about. And dynamical decoupling, which is kind of a quantum way of eliminating coherent errors in your system. And these are all things that you can introduce with Pulse, and then kind of I had made the slide before, and what I realized is that last week, this is like very, very fresh news, we achieved quantum volume of 64 on our systems. And so let me just take a step back and tell you that quantum volume is this holistic metric that we are using that essentially has to do with how large of an arbitrary circuit can we compute using our quantum computers. So we just published this and announced this on Thursday. And this is essentially an improvement to quantum volume. It was 32 before, it's 64 now. Where we're using only control and compilation to, sorry, question? Okay. Maybe it's background noise. So this was not with any hardware improvements. This was using the same hardware we had quantum volume 32 on, but it was made by improving the Qiskit compiler and then other methods I'll show you called excited state promoted readout, which means you can actually try and push the qubit from the 1 state to the 2 state so you can get better separation and classification between the 0 and the 1, or what was the 1. We have shorter 2 qubit gates, which of course improves because of the coherence. And we're using dynamical decoupling. And I'll kind of show you how this comes in at like a very low level. So basically, this is the idea of near-term quantum devices is you have hardware solutions and control solutions to all kinds of constraints. So you might have gate and measurement errors because you always will until you have error correction. So you can try and build more robust qubits or improve the microwave hygiene between your qubits or come up with a better frequency scheme if you can, which is difficult. But you also have control solutions. So you can try and calibrate your measurements better because that's kind of a classical thing that you can calibrate for. You can use, say, pulse shaping to get rid of crosstalk by doing, say, dynamical decoupling. For other examples, like hardware gate sets, you can try and make more interactions, like at a chip level, like you can couple more things together, but you can also do a lot of things with pulse shaping. Also, the number of parallel operations, you want to reduce crosstalk. This is something we achieved in software just using dynamical decoupling that's essentially done by pulse shaping. So all of these things have a hardware solution that of course we need to continue working on, but now I'm going to present today the control solutions. So basically what programming in Pulse comes down into is you have 4 kinds of channels. So you have the drive channel and the control channels that actually control and act on the qubit. The drive channels would be at the qubit's resonant frequency. The control channel would be off resonant drive, which is often used for cross resonance gates, but it could be some other kind of 2-qubit gate you could do. And then we have measurement channels that's at a different frequency, and that kind of comes at the end when we want to measure the qubits. And we have the acquire channel, which you don't actually apply pulses to, but that tells the digitizer when to start taking raw waveform data back. And then we have certain instructions we can do. We can play waveforms on the channel. So typically for the pulse channels, we can delay channels. So you can put time between the pulses, which is actually very useful because as an experimental physicist, your bread and butter is to come up with pulse sequences and vary one parameter and see what happens and fit it to a theory so you can figure out what's going on in your system. You can also shift or frame change, and I'll get into this again, but this is what changes the frame between the qubits. And if you keep everything together, then you don't have to worry too much about it. Your acquire channel just tells you when to start acquiring, which will then start the electronics integrating and classifying your system. So basically, this is just says something similar. You have the drive channel, measure channel, control channel, which actually have pulses played on it. They're mixed up to a microwave RF frequency and sent into the fridge, and then they come back, they're amplified, and they are scheduled on the acquire channel where they're then digitized and stored as registers. So this is basically kind of what I like to show. So on the left, you have something called, we call the circuit model of quantum computing. And this is a Hadamard gate on qubit 0 and a C0 from qubit 0 to 1. And what this does is generate the Bell state 0, 0 plus 1, 1. So what happens if you actually take that and you see what's going on the actual device level, you get what's on the right. And so there's a lot going on here. Basically, every one of these channels is labeled A for acquire, D for drive, M for measure, U for control. And so your acquire and measurement pulses are all happening to the right here. So we're going to forget about those and just concentrate on the pulse level, or, I'm sorry, the qubit control pulses. So what happens here is you can see where the frame changes are happening. These little circular arrows, they are telling you where we're shifting the frame of the pulses. So this will physically shift the phase of those pulses that are subsequent. And as Alex said before, if we keep those pulse changes aligned with those same kinds of cross resonance, with the cross resonance channels, then we just keep accounting, and we're able to do these frame changes naturally without worrying about it. So that's one of those tricks we do to reduce the error. But then we also have these things called drag pulses, which is derivative removal of adiabatic gate. This is a technique to try and reduce leakage on the pulses by adding a derivative of it to the quadrature or imaginary channel. We have an echo. So this is kind of a standard echo where we do a cross resonance one way. We echo the qubit and then do it the other way to try and get rid of dephasing. And then we also have rotary echoes, which will eliminate other kinds of interactions from the Hamiltonian, such as ZZ interactions, which are undesirable because you want to just get the ZX out of the Hamiltonian. So as you can see, there's a lot going on. And if you look at the paper that's on the archive as last week for the quantum volume 64, you'll see even more techniques that were used at the pulse level to try and improve the quantum volume of those devices. So I think that's very interesting. And there's a number of applications I just want to kind of go through relatively quickly. That I mentioned before. So error mitigation is one way we can try to amplify the error of the, we try to compile the best circuit we can for a given algorithm. And then what we can do is we can amplify the error. So if we just make the circuit longer, we can make it more susceptible to incoherent error. And so this is the idea behind something we did for chemistry called Richardson's extraction to the limit. And what this means is essentially I have an energy I'm trying to minimize right here, but the best my circuit can do is with this amount of noise C1. Well, what I can do is I can add more noise to it and go out to a noise factor C2, and then I can measure my minimum energy on that level, and then you can take the lambda goes to 0 limit and try to extrapolate to a new noise level. So it turns out this actually runs, but you have to calibrate these pulses up and then run them, but it does produce better results. For example, this is from a variational quantum eigensolver simulation of lithium hydride. This is energy versus bond length, and the dotted green is the exact answer, and the white dots are the experimental results. For this VQE, we could only go to a depth 1, so we couldn't generate too much entanglement because we had just too much error that accumulated. So we didn't get very good results. But what happens when you run the same experiment, but you go to a depth 3? Well, now for C equals 1, which is the best you can do at depth 3, you can clearly see that's worse than the depth 1 case over here. But now you can try and run it for more and more error and see what you get with the experiments. And then by applying this extrapolation technique, we're able to get to extrapolated dots that are much, much closer to the actual exact answer. And so this is a demonstration of how this actually works to, increase the performance of your quantum algorithm. We also have different measurement levels of the measurement data. And so, yeah.
Oh, since you were on that slide,
sure.
Do you foresee that IBM might, so let's say we have a 1024 shots, and you're running separate experiments with this at a pulse level in order to extrapolate downward. But what I'm wondering is, would there ever be like a possibility to have that done like along some curve essentially for the shots themselves? So if you were doing, if I were operating at a circuit level, and I could like specify some option where over maybe 10,000 shots, like that, the additional error in the circuit is going to increase automatically for me, and then there can be some extrapolation from that. because right now I would guess that this is a lot of manual like scheduling of multiple experiments and then classical post-processing, right?
That's right. And I think there are ideas to do this, because one of the things is we kind of have like a circuit model we call like quantum assembly, which deals with the gates, and then we have the pulse model, which deals with the actual pulses, and they're kind of like not really integrated right now, but we have ways we can kind of flip between each other. But I think in the long term, we want to make these more realizable so that we can implement these techniques into like a more circuit-based model. And you can just like send a flag and say like, do the extra circuits for an error mitigation. So I can't say when that's going to come up or if even, but it seems like a very reasonable thing to happen.
Thank you.
And I have a question also. I assume that basically calibration has been applied and they try to take into account, and still you get this kind of off the actual value, right? And it means that you have to do the this mitigation process with different values of C.
Right, different values of C, which, I mean, for this experiment, they were calibrated separately. Qiskit Pulse now has parametric pulses, so you can possibly apply scaling. Due to the intricacies of like microwave mixers and nonlinearity, so that you can arise there, you probably won't get the best pulses in that case, but you might get something good enough for like Richardson's extrapolation to work.
Okay, thanks.
No problem. Okay, so I'll just continue on. Oh yeah.
Can I ask you a quick question?
Sure.
I'm curious as how does this relate to your simulators? Do you try to run the simulator so that you mimic some of the profiling here, or does it work differently today?
So when running the simulators, I mean, there's all kinds of simulators, but typically what you'll do is you'll put in like depolarizing noise, and so that's kind of would work for this model. And you can kind of get an estimate of how well your variational circuit will run based off those simulators, which is probably good to do because VQ is a pretty expensive algorithm. All right, great question. Thank you.
Could I ask a question as well?
Of course you can.
So this actually goes to something maybe a couple of slides back where you showed this pulse diagram next to the circuit.
This one?
Simple, yeah. So it seemed to be what you were saying is that these channels all kind of have a fixed frequency, and then this diagram is showing the amplitudes along at those frequencies. Is that a way?
This is pretty much true. So I'd say I would say you'd have like, at least for the control pulses, you'd have 3 different frequencies going on right here, or actually, sorry, 2. Yeah, so for this one, what we're doing is we are, D0 is going to be at the frequency of Q0. D1 is going to be at the frequency of Q1, but U1 is going to be at the frequency of Q0 because it's driving through qubit 1 because it's the cross resonance pulse. These, echoes, these are all resonant as well. But this is the one where you're applying one frequency to a qubit that's resonant at a different frequency, but it's coupled to this qubit that's at the same frequency. So for like a standard thing like this, yeah, they would be all at the same frequency, but that's something you can change also in Pulse. It doesn't have to be fixed frequencies. So you can do like frequency shifts or sweeps or whatever.
So is the concept of a channel, is it both a frequency and also a physical location that pulse is getting applied to? Is that the idea?
Yeah, they can be. They're probably going to be, it's probably going to be the same channel coming out of a waveform generator in most practical purposes. It doesn't have to be. They could be combined later. But essentially, these will be combined. D1 and U1 will be combined physically and go to qubit 1. And then D0 and U0 not pictured will be combined and physically go to qubit 1. But the 2 qubit interaction is the one that's happening between this 1 channel and this 0 qubit.
Uh-huh. Okay, I think that makes sense. So
great.
Yeah.
Yeah. It takes a little while to get your head around cross resonance. So there's a lot of pulses, and actually I've been having fun breaking these down and trying to figure out how to run them better myself, because you can see how using shorter pulses might be able to get you higher resolution, or you'd be less susceptible to error. So you might be able to improve your error budget if you could make these pulses shorter, for example. But the amplitude of these pulses is usually calibrated due to what's the shortest I can make them without getting too much leakage. So it's kind of like the minimum you can do with a reasonable error rate.
And you get leakage, I guess, because you're applying too much energy.
That's exactly right.
On that channel, is that?
That's exactly right. Yeah. And so those are the kinds of things we use to calibrate. And in fact, it's shown in the paper that's on the archive from last week. You can see those exact curves that we call them tick plots, about how you choose what length to make these cross resonance drives at. But yeah, so this is all stuff you can play with yourself as well.
And that's in the volume 64 paper, that's all?
That's in the volume 64 paper, that's absolutely right. Let's see, other applications besides error mitigation, but this is, an important one. This is actually, a classical technique. There's certain kinds of, waveform level data you can get back from your measurement, for example. So right now, there's too much data for us to transfer. We're still working on this, but we call it level 0 measurement. Is like a raw waveform that you get mixed down to an IF frequency of tens to hundreds of megahertz or something. So typically what happen with that data, what happens on the computer is you integrate that waveform with some sort of kernel. So we call it kerneled data, which is level 1, and you integrate it to essentially average over some point in the complex plane, or we call it the IQ plane, which corresponds to your measurement. And so that's an IQ point. And if you're measuring zeros and ones, you tend to get these blobs or clusters of the I and the Q. And then you can imagine, well, I want to tell the difference between 0 and 1, so I discriminate in some way. So in this picture, just I'm showing you, you can draw a green line and say everything on the left is a 1, and everything on the left is a 0, everything on the right is a 1. But you could be much fancier. You can draw other kinds of things. You can build distance of Gaussians. You can do machine learning. You can do all kinds of things. And in fact, with the excited state, second excited level state readout, that opens you up to a lot more classification possibilities, because you have more blobs to deal with. You'll have 3 instead of 2. So we'll see how this goes, but this is very interesting. How do you do, and that I got to say, that improved the measurement field quite a bit, just being able to classify these things better. So it's not always just like the physics. Just to show you kind of what you can do with the measurements is you can do a small measurement where you don't get much separation between the 0 and the 1 states. And as you increase the measurement length and you integrate to some degree, you're going to pick up more and more information from that measurement, to the point where you can relatively well classify them, and it doesn't get any better. And in fact, due to relaxation, it'll get worse. So you can play with these things and try and optimize these things. And this is even messing with the pulse shape of the measurement, for example, which is something we've done in the lab as well, which you could also do with OpenPulse. We can look at the higher order levels of the transmons. These are useful for other things, not just readout. So we've got the 2 right there. There's some applications. So we can measure the energy difference between those 2 states. This is something we call the anharmonicity. It's related to a device parameter called the charging energy. And that's just good to know from a device physics point of view, but you can think of other gates that use that higher order level, or you can make a Q-trit or something like that. So there's some ideas of having a Toffoli gate using the higher order level, essentially by doing like 2 cross resonance on either end and a cross resonance in the middle between the 1 and the 2. Other things you can do is you can excite your state into higher order population, so you can get some really good contrast to measure the temperature, the effective temperature of your qubits. So the residual excited state population is given by this Fermi function here, so you can extract the temperature. And then I mentioned using optimal control, you can do leakage reduction. So this is a thing, instead of using the normal drag pulse, which is in the dashed line, this group used piecewise constant functions and optimal control in order to make a 4 nanosecond single qubit gate with higher fidelity than we have typically in the lab. So you can improve a lot of things using a lot of these techniques. So I guess in general, brings me nicely to my conclusions, is that this pulse level access allows you to squeeze the most out of the performance. And in fact, like I think the QV64 paper from last week really shows you how much this control has an effect on the ability to do things. or to do computations well. But of course, it's both hardware and software that we need to focus on. And so, we're in the lab designing new hardware, fabricating new hardware, building better fridges, but we also need to come up with more ways we can control things in different ways of optimizing for that control, and then coming up with different metrics that, device level metrics usually tell us about one or a few things, but the overall system metric is something we're also continuing to push forward. So I'd like to thank you very much for your time, and if there's any remaining questions, I'm here.
Yeah, I've got one for you.
Sure.
What are you most excited about that you haven't been able to dig into yet in terms of, I'm sure you've got a lot of experiments you'd like to try. I'm just curious, like knowing that like not all of them will pan out. I'm just wondering where your intuition is about what you're excited about doing next. So
I think tailoring these cross-resonant pulses to more use cases is something I'm thinking about, but I'm already like, I'm not going to say I can't do it yet because I'm trying to do it right now. Other things are a more level of control and feedback is something that I think we'll see progress on, pretty soon, but it's a little hard. You'd like to have like an if-then statement in your quantum program, but right now you have essentially all your control first and then all your measurements afterwards. But this is something people are working on. So I think that's probably I've been waiting for that for a long time too. So that's tough. It's tough.
I'm wondering, can you kind of explain again what was the main component that increased the quantum volume to 64?
Oh, absolutely. So I didn't put in, I only just made this one slide for it. I didn't go into the details of it, but I hope, we'll have maybe on our Qiskit YouTube channel a talk about the quantum volume 64 paper soon. But it was essentially all of these things. So essentially you're trying to do, so the first thing is improving the compiler, which I didn't talk about. Basically, quantum volume is judging what's the size of a random quantum algorithm I can do. A square-sized algorithm where each component is a qubit or a random unitary between two qubits, or between any qubits, I guess. Then you have to map it to the ones that are actually there, your actual architecture. So the thing that was done in this compiler was figure out better ways to map those random circuits onto the qubits that actually exist. So for example, our superconducting qubits don't have all-to-all connectivity. Right now what this is ran on, this has something called a heavy hex connectivity, which means we have it looks like hexagons with qubits between each point on that hexagon. So like each edge has an extra qubit. So you have to figure out how to map something where there's arbitrary connectivity to something that has limited connectivity. And that's essentially one thing that was improved with the compiler. This excited state readout, it promoted the assignment value 0 and 1 became much better. So that doesn't just help your measurements, but that also helps your calibrations, because you can get more out of your calibrations if you have less error rates. The shorter 2 qubits gates, this is probably one of the hardest things to do. We've been getting better and better at it, but the 2 qubits gates tend to be where most of the error happens. And by making those shorter, we are able to, I think we went from 280 nanoseconds to 200 nanoseconds for your average 2 qubit gate. It's all in the paper. I'm just trying to pull it from my head. Oh yeah, and by the Qiskit compiler, they were able to cut down the number of C naughts from like 9.4 C naughts, which is the 2 qubit gate, 9.4 C naughts per unit of depth to 7.3 using the compiler. So you save a lot of C naughts, and then saving 80 nanoseconds off those C naughts may not sound like much, but it is a lot when you have a lot of them. And then dynamical decoupling scheme is what we realized, and actually we published a paper on the archive recently about the rotary echo technique that we're using. And essentially what this does is, if you keep all the spectators busy, they have less time to mess with your operations. That's what I'm going to loose framing of the situation. But if you read the paper, you'll find that it took all of these things to get up to quantum volume 64. No single one of these is what did it. But these are all control things. The important part is you needed all these 4 things, but they're all control things. They're not hardware things.
Thanks.
No problem.
Hi, Nick. Thank you very much for a great presentation. I have a question on, in general, on the superconducting qubit. I think the qubit is operating under very low temperatures, like a few kelvins.
That's right.
And there are higher temperature superconductors. Why are we not using the high temperature superconductors, but instead it's very low temperature ones?
Yeah. That's a great question. A lot of it has to do with the high temperature superconductors are very difficult to manipulate, very difficult to fabricate. They're usually made out of they're like cuprates, for example, which is like your coffee cup. So you can imagine how hard it is to kind of fabricate that and turn that into something, especially growing like a oxide layer between them. Whereas metallic ones that are typically used these days are going to be a little bit more malleable. They're a little bit easier to process and things like that. So from what I've heard from people that are experts in fabrication, it's really hard to get a uniform oxide layer between these things, and they're really hard to manipulate to begin with. That being said, there are people that are working on this. This is definitely an area of active research. You know, essentially everyone makes aluminum oxide junctions because it's easy to make them, and we can take that pretty far. But there's also a lot of people in, you know, especially in universities that have labs that are doing much more, you know, highly controlled growth techniques in which to make more pristine junctions, which could maybe eventually include high temperature superconductors.
I see. Thank you. Thank you very much.
Yeah, no problem.
Any other questions? If not, let's thank Nick again. Thank you, Nick. That was awesome.
You're quite welcome. Thank you. Thank you for your time.
And
questions.
Before we go to the second talk with Andre, I just want to ask again if anybody got any announcements to make. Looks like not. So then we welcome Andre Koenig, a man of many hats. I think you have your affiliation as interference advisor and other. So please, you know, introduce yourself and tell us more. And we're eager to learn where the money goes in the quantum landscape. Andre.
Absolutely. Thank you, Alexia, and thank you, Nick, for that great introduction or refresher for some, and congratulations on the quantum volume. I know IBM is committed to doubling that every now and then, so looking forward to 128 soon. I'm a data kind of guy, and I'll do a quick introduction. This gentleman that many of you probably won't know, Edward Stemming, he comes out of the manufacturing sphere and quality around manufacturing. Said this very famous sentence: if you're in this kind of thing, without data, you're just another person with an opinion. And that is kind of the underpinning what I do. We'll be looking at a few slides, but very quickly move into some of the actual data. Myself, I do wear a lot of different hats. I mentioned earlier, I was a management consultant for 12 years with the big houses, starting with Anderson Consulting in the late 90s. Accenture, SSA and Company, and so forth. You see some of the customers I worked with, many of them at the senior executive and C-suite level. Went to a bunch of schools to study mostly economics and business. The first one, University des Saarlandes, a German university where I'm from, studied economics, finished the degree at the business school ICN in France. Then got an MBA at the University of Chicago. And unfortunately, I'm not smart enough to ever dream about getting a PhD from MIT. So I just took all the quantum computing classes to at least get a little bit of sense, and bought a big golden frame for my certificate to show off a little bit. If I don't do data, economics, and all these things, you'll find me on a sailboat. One of the reasons I live down here in Miami. Here you see me competing in a national championship 5 years ago. Today, mostly cruising through the Caribbean, drink in hand. I run 3 companies, all of them within quantum technologies. Interference Advisors is kind of the Gartner of quantum technology. So we collect data sets, produce insights, and write market research reports. We've been doing that for over 3 years now and the leader in the space. One Quantum, the second company, is a community organization organized in chapters. We have a startup chapter currently with over 30 members and growing, that we only launched a couple months ago. A Women in Quantum chapter, where we had a big conference a couple weeks ago to kick it off with 652 attendees. We reached over 150,000 people online, had 16 speakers over 3 days of content. So trying to build communities around themes, around geographies. We'll hopefully be starting Quantum Africa soon, since I have a small team in Africa, to build community from anybody in academia, business, entrepreneurship, vendors, government, investors that works within Quantum. Lastly, I'm also an investor through my fund Entanglement Capital, where I'm currently working on 2 deals, a $3 million round for a quantum tech specific startup accelerator, kind of the follow-on program to the destructive construction lab in Toronto that was mentioned earlier, as well as a 60 million euro quantum computing hardware deal that we're currently trying to put together for a European company. So those are my 3 hats that I wear. Everything that I do, going back to Deming's, is motivated by this idea of data. And this is a very difficult topic, but I'll always remember one of my professors from Chicago, Richard Thaler, who introduced us to this cognitive bias codex. And there is research, the better you're educated, the more professional and life experience you have, the more prone you actually are to having these cognitive biases. Things like an anchoring bias, where when asked for a specific number, and somebody said 314 startups when we did our little poll earlier, is probably anchored to a number that they previously in a different context heard. So you see this codex, there are many different types of biases, heuristics, and anchors that we unconsciously use that inform our decision making. I certainly do that on a daily basis. So really hoping to bring data, insights, facts, analysis to try to mitigate that as much as possible. And really mostly for the investor space, that is my main target. And that is what we'll be looking at a lot here during the next few minutes. We really see that a lot of the investors do not understand the purpose and the sense of what quantum can do as a technology. They also don't understand the market and how to scale it on a revenue basis for a specific exit or different exit scenarios that might not be based on a revenue type model. And the technical details here matter, but also the data matters, because there's a lot of hype. There are a lot of people out there that are very loud. We don't just have noisy intermediate quantum computers. We also have noisy intermediate quantum startup founders, and we need some data to fact check them. So the idea really is, to collect that data, not just provide tables and articles and news, but really try to understand what insights we can garner out of this data, and hopefully turn it into wisdom for our clients, which are investors, but also regional governments in North America and Europe, as well as vendors and some of the large startups. The way we do that is we actually have a methodology and technology to continuously collect data. There are 2 things that we don't do. The first one is to simply write down any kind of data that we hear. I'm sure all of you hear about startups or qubit count or qubit volume. There's a lot of blogs out there that kind of collect that. That is not how we approach it. We actually systematically parse, public as well as private sources of information. We have methodologies to go through social media channels, private networks, but also conferences to methodologically collect this data. The second thing that we don't do is consider data that is not verifiable. So everything that you'll be seeing in a couple minutes here is verifiable data. Verifiable, I mean, it's data that can be proven publicly because there's a website, something on LinkedIn, a press release, an investor that backed it, or a private source that is able to verify it. What we do not consider is, again, hearsay, opinions, claims, assumptions, and so forth. We really try to stick to the facts. Then obviously we're not perfect in that, but getting better every day is the ambition and goal here. We then look for insights. And how do you look at insights? It really has to do with looking for extremes, for tail ends, for spikes, for anomalies, looking for changes over time, looking for relationships, looking for gaps. So we actually have specific frameworks for much of it. Yeah, some of it we do by instinct or habit still, unfortunately, but a lot of it we have spreadsheets where we look for certain of these potential insights. We score them according to a system, and then we see what comes out at the end. So methodological effort to look to derive and arrive at these insights. Ultimately, the last step, and I'll show you one example, is to use all of this data and the insights, but also our networks that we have to produce market research reports, similar to what a Gartner, PitchBook, Crunchbase would do to inform the decision making of investors, government officials, enterprises, clients, and so forth. The last important step in achieving that is the importance of data visualization. And I mentioned that not just showing tables or simple charts. And this is really something that we're pushing every day, and we still have a lot to learn and a lot to improve, but making the data as interactive, intuitive, personalized, and collaborative as possible, so that we can do a better job at arriving at insights, and our clients get a lot more value out of that data by interacting with it. And a very simple example, this is not quantum related, just a typical HR table, like you would see it in an Excel spreadsheet, certainly something I've done for many of my startups. And then an example of something, color-coded, filterable, searchable, sortable, that is a lot more visual and insightful. And this is obviously just one example of what you can do, but the importance of data visualization in arriving at insights and meaning is really key, and something we focus a lot on. That concludes the slide version. This deck contains many more slides specifically geared at investors and how investors can make better decisions within quantum tech and startup ecosystem. Here we propose a segmentation framework for the entire quantum system, how to benchmark quantum tech deals, which is very difficult because there really is no precedence. It's a young industry. How do you get a quantum tech pipeline, deal pipeline as an investor, and how do you evaluate it? How do you ultimately make your investment decision and successfully operate your investment? So we propose a lot of frameworks here. We'll be sharing these slides if anyone is interested in that. But let's go look at some of the data. Get this out of the way. All right. Get rid of this. There we go. So we asked this question earlier, how many startups there are in quantum technology. And again, looking at the whole quantum information science space across quantum computing hardware, software, but also sensing, communications, quantum key distribution, and other applications. We have a little chart here that shows how this has evolved over the last 3 years. And a couple interesting takeaways here, in my opinion. Number one, the space has grown significantly since 2018 when we first started tracking it. But in 2018 already, it was a very significant space. I don't know if it was 314 total, I'd have to check. But in 2018, there already was about 300 to 350 startups globally that we were able to verify and track. As you can see, and I'm highlighting quantum computing hardware here, this has grown, but it hasn't exploded over the last 3 years. It is something that has naturally grown and evolved as the technology and the market has matured, but really took its first steps already years ago. The other interesting, in my opinion, inside here is that we have a very large number of quantum software algorithm and simulation companies. Sometimes it's hard to distinguish amongst all the marketing talk what a company really does. Do they just do algorithmic research? Do they actually write software? Do they ultimately do simulation? But there's a very large ecosystem of, let's call it, quantum software startups, and we have a separate category for only quantum computing software startups here. So if you combine these two, there's more software out there than hardware, which I find very interesting, considering that it is an industry that is still young, a technology that still needs a lot of development and breakthroughs. If you compare this to classical computing, I wouldn't be able to say how many software companies there were 50, 60 years ago, but certainly far less than hardware, I would assume. So this is a very interesting finding. If you look at some of these other categories, you see that overall they are much smaller. You see that the growth is much lower. And you also see that there is more and more folks like me, and that might be a good or a bad thing, consultants, think tanks. Today we actually count almost 40 of them worldwide that specifically do consulting and a lot of hard thinking about the business side worldwide about quantum computing. A lot of media outlets that have sprouted up, and then some other companies that do quantum learning and other kind of aspects of quantum technology. So this is kind of the ecosystem. Unfortunately, it is very difficult to get data out of China and Russia, at least verifiable data. So take that with a grain of salt. If you look as of June 2020 at the geographical distribution of it, no big surprises here. Obviously, North America and Canada, the US, leading here in terms of the number of startups, 122 in the US, 43 in Canada. Europe, and this is surprising to many, in aggregate has more than North America, and individual countries such as France, Germany, Italy, and others are growing very strongly. The UK, if you look, even so they left the European Union, other than the European context, we currently count 64 quantum tech startups. So a very strong and strongly growing network of companies there. Very little activity, unfortunately, in Latin America. I mentioned our friends at Quantum Files with Martin and Raphael. 3 companies in South Africa, a very good university there. We then do have some activity in Asia with India and China. We have only one truly verifiable startup in Russia. Obviously, there's a lot more than it, and I think everybody knows that Australia is very strong. The startup ecosystem, so still relatively small. Japan, I'll be very transparent. We haven't done a great job at collecting data yet. Nonetheless, we already count 17 startups to date within quantum computing. We also have the breakdowns by applications, so if anybody is interested in quantum computing versus sensing, communications, encryption, software or hardware, we can look at that separately. So that's to get us started, some of the startup ecosystem. Next, we'll look at the market, but wanted to see if there are any questions at this point.
Andrew, I just have a question. So, so basically, the coloring are upper brackets, right? So 20 means up to 20. So when you look at South Africa, it's 3, but so it's colored that 20 colors. It's under.
Correct, and we can change the granularity. Good point. Actually, maybe an opportunity here to make it even more granular in 5 increments or whatever. But that is right. Yeah.
And one more question. So obviously, there's been a few years, and half-life of startups sometimes is under 2 years. Do you track this historically? Can you move in time and see which startups were born, how many died, in a given time period?
Great question, and that's exactly how you get into insights, right? Tracking this over time, looking in what regions certain companies are evolving. Are they getting a specific type of capital? Do they work in a specific QIS application? Or are they dying? And we have what we call a graveyard. So we do have a whole table and charts of quantum tech companies that are dying. There aren't too many at this point, and we haven't seen any trends in it yet. We haven't also focused on that piece of analysis yet, something that's on my to-do list. My opinion, if I can have an opinion to say something against what I just presented, is that there's no insight in what has died or not survived so far. We definitely see very interesting trends as to where hardware or software is stronger in certain regions, and how certain regions might do more quantum communications versus quantum computing and those types of things. So that's surely available.
Interesting. You mentioned a startup, one verifiable startup in Russia. Is it by any chance called Qurate? Or is it something else?
I'd have to go into my database. The name doesn't ring a bell right now. I can check that after this call.
The Qurate, yeah, these are folks from Skoltech, which is the innovation hub near Moscow, and actually they were in our conversations and offered to speak about their work. So I'm just kind of making a connection here. They are an interesting company. Yeah, so cool.
Well, let me
awesome.
say this. So I have a small team of folks that help me collect, clean, analyze the data, write and produce insights and reports. I'd love to find somebody in Russia and somebody in China who can do that for the local market. So if anybody has referrals here, send them my way. We'd love to explore those markets and get better data.
Absolutely, I'll do so for Russia, and if folks can do it for China, we'd appreciate it too.
Awesome, thank you. Also a question, and we're slowly moving, towards the investment side of things, but just looking at the global market, right? And there have been a few exercises out there in terms of sizing and forecasting the quantum information science market. Many of you might have seen the Boston Consulting group effort from 18 months ago. Obviously, tremendous piece of work. There are other, market researchers out there that estimate the market. We build a model, which I'll show you in a second here, to really do custom market size forecasting for quantum information science. And what we're forecasting here is the revenue potential for quantum information science vendors, which might include, our friends at IBM and their competition, startups, and so forth, in commercializing their products and solutions. There's another type of market size forecast that we could do and hopefully will publish soon, which is the impact that quantum technologies will have. We mentioned JPMC a few times during these conversations already. JP Morgan obviously has a huge program. The impact that quantum technologies could have at JP Morgan, other banks, chemistry, and so forth, far exceeds the revenue forecast potential. And I think that would be very interesting to look at. If we look just at the market size forecast for revenue, and this is a very conservative scenario, you'll understand in a second what I mean by that. We estimated at $172 million for this year. We estimate that by 2030, annual revenue potential will be around $2 billion and a compound 10-year market size in terms of revenue of $9 billion. You see a red and green box underneath where we do a little bit of scenario planning. So this is what we call the base scenario. If we look at the low scenario, those numbers go down. Year 1, 2020 doesn't change, but 2030 obviously a lot smaller, and those are the compound growth rates kicking in here, and a total market size that is only a third. If we slightly improve our assumptions and make them slightly more optimistic, there's really an explosion in the market size potential. Year 1, 2020 obviously doesn't change again, but you see that in 2030, we have a slightly larger market. The compound, however, is really tremendously more significant, and that is the real insight here. We'll look at some of those assumptions in a second. Here for this base scenario, we also have a breakdown by QAS application. Quantum computing, no surprise, makes up the bulk of that forecast. Quantum encryption already is a market today. There are already companies that make significant revenue to the tune of 10, 20, 30 million a year. Quantum sensing, quantum communications, and other things, really only take a small share. Let me actually show you, and this is something that very few people see, the model behind it. There's a very large, let me move my speaker thingy here, a very large and flexible model that is based on a number of variables and assumptions by number of customers, average price, market size, and so forth. What we do in this model is that we segment it in applications. Quantum for finance, quantum for chemistry, quantum for logistics, machine learning, new materials, encryption, and so forth. So we have all the potential use cases that quantum could deliver, because that's where the revenue comes from, right? The revenue doesn't come from a quantum computer itself. The revenue comes from JP Morgan buying cloud credits or service level agreement from IBM, or eventually an on-premise quantum computer from somebody else. So that is how the model is structured. We then estimate hardware on-premise sales, and there is some in 2020, which surprises many people. We look at hardware service level agreements, which is something that large vendors tend to do, where they give you a 1-year, 2-year, 3-year contract for access to their hardware, which also includes software, which also includes services, joint research projects, and these tend to be fairly large service level agreements. There's a lot of, we looked at that just a few charts ago, software companies out there, as well as simulation companies. They tend to sell smaller product solutions, platforms, maybe for $50K, $100K, $200,000 a year. And then you have hardware cloud, right? We've all been on IBM, Amazon Bracket just launched, Rigetti, where you all have, you have a free layer. You tend to have a free layer. That seems to be changing for some of these vendors, but then you have to swipe your credit card to continue using it. So here you can estimate the number of customers. Down here you can estimate the average price point for each of these, and you can estimate the growth rate. The conservative base scenario that I showed to you earlier in here is based on the smallest assumptions. So, really starting with one customer in 2020 per all of these segments, the lowest price, which is, as an example, 15 million for an on-premise hardware computer. I believe there will be 3 or 4 sold this year. One has been sold already. And the prices were around 20, 21, 22 million. So these kinds of very conservative assumptions, and then a growth rate for all 10 years, which I had put at, let me check, at 30%, which I believe to be very conservative. In the low scenario, the growth rate is 10%. In the high scenario, the growth rate is 50%. So this is how this model works, and this is how we estimate the market. This is also how we work with customers who might be interested in predicting, forecasting a specific segment of the market, quantum machine learning, or quantum computing cloud, and we can very easily and reliably do that with the scenario planning tool. Questions?
Andre, I've got a quick question, if I may. Do you have any data to form a view on quantum annealing potential versus universal quantum computing in the market? Do you see a difference between the market that these two paradigms are in fact addressing? And do you have a view on this?
Yep, great question. We do look at the D-Wave and such in some of the investment data that we'll be getting to next, and for very specific reasons that we'll explain. So yes, we do that. In this market ecosystem where we started and market size forecast approach that we're looking at right now, we do not include annealing. Obviously, it's a big debate, right? Is annealing quantum or not? I think it's a little bit of a silly debate, to be honest, because at the end of the day, D-Wave has a lot of customers and really delivers value for them, and that's what matters. But that said, we did not include it in the ecosystem slides you've seen so far, or in this forecast model. I also don't have reliable revenue predictions for annealing, no.
Thank you.
Good. So we've looked, giving it away here. We've looked at a little bit of the ecosystem. We looked at how we think about the market and how the market might evolve. So by the way, I didn't mention that. We have 542 quantum tech startups in our database so far. So we're in between the 100 and 1,000 that all of you estimated earlier. To give you a little bit more of a sense, that grew by, I'll say about 75 over the last 3 months alone. So, a significant growth rate for one part. Another part that we are getting better and better at finding these companies, verifying them, and including them in our data set. So it is an ecosystem that is growing strongly. It's not exploding as we showed in the first chart, the bar chart. And it is a very large ecosystem, but we're not at the 1,000 startup mark yet. I also asked you to estimate the USD investment amount for 2020 so far. And here it is, all the verifiable investment deals for the first and second quarter of 2020, $386.5 million in private capital. These are not grants, these are not government programs, but private investors that have invested into any of these quantum information science. And this, to your question just a minute ago, would include annealing and D-Wave if they get any money, is the overall amount invested so far. And this is a very large amount. If we look at the trends over the last 3 years, a little smaller, the overall fundraising amount that is verifiable, again, we're only looking at verifiable data, right? I'm sure there are rounds out there in fundraising that haven't really been announced, that might be rumored but aren't verifiable. We don't include them. All in all, you see that total investments on a yearly basis, somewhere around the 600, 700, 800 million a year. 2020 in the first year, we are close to 400 million, and that during the biggest crisis that any of us has ever been through, and where many other sectors of the economy really suffered in terms of fundraising. So to me, this is a great sign. I don't know who still talks about quantum winter, but from a financial point of view, the first 2 quarters of 2020 clearly have proven that there is no quantum winter, and very significant private funds flowing into the market. You also see the distribution here by QIS application. Quantum hardware is getting the bulk of it. Quantum software and QKD. We haven't seen much in communication sensing or other fields at this point. If we look at, and this is interesting, at where their investors come from. So these are not the target companies, but the country of origin of the investor. No surprise, America, the USA, is the #1 country here. And that is going to be a long time before it changes. This is the number of deals, so 26 deals made by American private investors. But interesting here is a couple things. You see countries like India starting to invest, in Japan, you see activity. And then when you look at Europe, and again, Europe in aggregate, 5 deals by French investors, 3 deals by German investors, Finland, Norway, and then again the UK with 10 deals. We're kind of exceeding American activity in terms of where the capital comes from. And this is very, very interesting. If you're European and German like me and a founder, entrepreneur, it is always this complaint, and justifiable complaint, that it is so hard to raise capital as a European entrepreneur in Europe. And that certainly has been true in digital, in SaaS, and artificial intelligence, blockchain. It is not true in quantum, and that's a big surprise. European investors are very, very excited about quantum, and they are opening their purse strings. Something that is not on the map here, but I'll mention it. Israel is something that everybody needs to watch. A lot of stuff is happening in Israel, and that's going to be a big, fat, dark blue spot on the next edition of this map. Any questions, comments? We'll look at the next chart, which looks at the target countries. So where these deals are being made. And that is equally interesting. Obviously, again, the US is #1 here, but only with 14 deals. So we had 26 investors or investments out of the US, but only 14 deals being made in the US. And that only leaves us with Europe, right? And really a lot of deals currently happening in Europe. We have some in Australia. Canada is always on the map and always will be. But here also we see that the deals are being made in Europe increasingly, and even foreign capital is moving into Europe, which is unusual at such an early stage of a technology. So American and other foreign investors investing into European hardware, software, QKD companies. So far, so good.
I have a question.
Go ahead.
So looking at this map and then the previous one, there seems to be more sources than there are targets. Could you explain what's going on?
Absolutely. If you're a company, you're going to have many different investors, right? It's
Right, yeah.
Hard to have only one investor. You typically have what's called a lead investor. Say you raise a 10 million round, that lead investor is going to take 3, 4, 5, 6, 7 million, and then find co-investors, other people that fill up that round. So, an investment round can have anywhere from 1 to 5 to a dozen investors. You're definitely going to see 5 to 10 on average. So that explains that gap.
Mm-hmm.
All right, let's look at some of our other data. Top 10 quantum tech startups by funding so far. Everybody read about PsiQuantum. Hopefully that is no surprise to anyone this year. Really amazing with $500 million. This goes back to the question earlier annealing D-Wave still in a solid second position, but I'll have a remark to that at the very end of my presentation in a few minutes here. Rigetti just announced roughly 80 million by a very large new professional venture capital fund, Bessemer, but also other co-investors. So Rigetti really progressing quickly. Our friends out of Cambridge continuing to do very well. You notice ID Quantique, so quantum encryption, but this gives you a sense of how much certain companies raise, which is very impressive. But for somebody like me who has worked in SaaS and software artificial intelligence before, these are fairly small numbers. And the fall off, if you start to look at the IonQ and then ID Quantique, these numbers for top 10 list get relatively small very quickly, and then you see Xanadu in 10th place here with 35 million, and then very long, very flat tail if you look at the rest of that list. So there's still a lot of room for improvement. Yeah, that concludes the investment part. I have one more investment kind of finding that I want to share in a little bit. I'll show you another couple ecosystem slides. Any questions before we move on? All right, so I'll show you some of the other things that we track. Obviously we just had a great presentation by Nick. IBM is the king of the hill when it comes to quantum computing, but quantum computing performance and access to quantum computing. So here you see a little distribution of qubit counts, also by modality. We have maybe more interestingly, I don't know if that's the next chart, it is quantum computing cloud access. This chart surprises many. There's a lot more quantum computing cloud out there than many think. Everybody is familiar with our friends at IBM. We all know that Rigetti obviously has access. Amazon is out now with Bracket. So nothing new there, but there's a couple dozen other very small offers that come out of overseas vendors, universities, and so forth that offer quantum computing cloud access to mostly their own hardware, and then you have some reseller relationships such as CQC, who provides access for preferential terms to the Honeywell hardware, for example, that are part of that list as well. But this is kind of the whole quantum computing cloud access market with a total of 29 players to date. We then also, for our clients, start to dig down into some of the applications. Here's an example of quantum chemistry startups, and we currently count 20 that specifically state as their mission to do quantum chemistry. Obviously there are many others that also do quantum chemistry amongst many other things, but this is just an example of how we try to look and segment the market. Here we have a chart where we look at head count, and this is also interesting to track the evolution over time, comparing this to the previous 6 months, a year ago, and so forth, of how companies are evolving. Very difficult to find data here, right? So this is to be taken with a grain of salt. But if you look at it consistently over time, it does tell you interesting things. So we go by LinkedIn and look at head count. To me, it was surprising to learn that one Qubit is the largest company here. You see folks such as StrangeWorks, a number 9 spot. Great company, but to me it was surprising to see them so far up. A lot of these startups are still very small. That is one of the key takeaways. of this here. Another second key takeaway is that there are other startups that I know are bigger that didn't make the top 10 list, but they don't report those numbers. And I spend a lot of my time encouraging some of these founders to do a better job at that, frankly, at the storytelling, at the messaging, at their information sharing, because this is the kind of information that folks like us look at, you know, customers, government, investors, and so forth. And if you don't share some of that information, you just make it, you know, it's an additional complication to overcome beyond understanding your qubits and your error correction or whatever else in terms of assessing the viability of you as a provider, potential partner, or investment target. So those are the two key takeaways here, but all in all, headcount is still fairly small.
Could I ask why QSoft is in the list there? I thought this was an academic department only.
Good question. Sometimes it gets very, very difficult to, and that's then my own freedom of decision making, to decide if somebody is a company or not. QSoft has a lot of commercial aspects. They have a commercial legal entity. They have commercial offerings. It is very hard to tell if they actually are a real company or not. In this instance, I decided that yes, but many times that is very unclear and still, you know, hard to tell. So there's a little bit of a judgment call here. But QSoft is commercially very active. One more. Oh, and okay, so sorry, this actually was just the top 10 quantum software startups by employees. I reversed the slides here. The top 10 quantum tech startups overall, that's the chart here. So that picture looks a little different, a little higher headcount, albeit not by much. We see some more bigger and familiar names. We still see a considerable fall off in headcount for top 10 list here, which indicates that there's a lot of room for growth left. No QSoft on this, so that's good news. These are definitely all commercial companies, but again, you know, information is difficult to get in this sense. But you compare something like this to funding, to you know, number of publications, which is something that we track. We track patents by companies and so forth. So these are all small puzzle pieces in an overall picture that we're trying to paint. And in that sense, it is, you know, one very important insight, but obviously not a deciding factor. All right, something else.
Andre, I just wanted to interject. You know, I've been in a lot of software startups, so it's interesting. You know, these numbers may look small to somebody who worked for IBM for a long time or like is used to, you know, big companies, but in kind of Bay Area, these are all huge startups, right? Because you start like with a couple founders. If you grow to 50, it often means you have at least 25 million investment, right, from a top VC firm. So like this is all, to me, they look like awesome. Like, you know, 200, obviously it's you know, it's near unicorn. Like you have companies like Databricks with multi-billion-dollar valuation software with 800 people. So just to put it in context, you know, this all looks very healthy and promising to me.
You're absolutely right. Thank you for bringing that up. You know, as soon as you have more than 40, 50, 60 employees as a startup, you start to be a very, very serious startup that at least has raised, you know, 50, 100 million and so forth.
Yep.
Absolutely, it's a very, very good point. So two more things that I want to show to you, and then we're done here. We have different databases. So far, I've shown you, you know, data and insights out of two databases. The first one, which we call our entity database, and entities can be a startup, a research lab, and we have, you know, the same kind of insights and visualizations for research labs. could be government entities and so forth. So that's our entity database. And I showed you some examples there. We have an investment database, and that's where we keep track of all the dollar amounts, the deals being made, who the lead investor is, who the co-investor is, and so forth. We have two more databases, and I'll show you in exclusive preview some data from one of our third databases, which is the quantum computing use case database. So we track all use cases, again, that are verifiable, that either have been published, reported, or been verified in private by the key stakeholders. We track what the use case is, who the vendor is, who the end user is, what industry, what country it is in. So this is a very interesting list. And when you start to dig down into this a little bit, we talked about finance and banks earlier, and I think, Alex, you made an observation about that. You will very quickly notice, and here's an example on page 3, that financial services, banking, insurance is absolutely the dominating sector in this use case kind of research that we do. So just wanted to share this with anyone, with everybody, but this is kind of another point of view that we take at the industry. All right. Everything that I showed to you right now and a lot more is available for free with a caveat on our QIS data portal, qisdata.com. So you can go here and find a lot of these charts for free. What you will notice is that we typically give last year's or previous year's charts away for free. And you can simply download them from here. If you want some of the up-to-date current charts, custom charts, or more highly segmented charts, then that is for our paying members, where we have kind of a subscription portal to access that. So any of these free charts, feel free to use them if you do your own sales pitches, investor pitches, whatever. If there is a paying chart that you're really interested in that you don't see here for free, just send me a message and we'll figure out how to get that to you. Lastly, we use all this research and all this data to ultimately write reports. Here's a report that just came out this week by one of my senior analysts, Farai Masandu, which looks at investment trend analysis in quantum information science. And here we get back to the D-wave question, and we'll end on that. One of the big insights is that if you look at the data over the last 3 years, let me make this a little bigger. Nope, can't right now. If you look at the data over the last 3 years, investments have very aggressively shifted away from annealing into superconducting, but also trapped ion and photonics. Annealing seems to have reached, I'm not going to say the end, but the peak of its fundraising journey, and really more of a reliance on revenue if they can succeed with that. But maybe we'll be surprised by another big D-Wave fundraising deal. But really the main activity over the last 3 years, and that is something that started over a year ago, has shifted into a real quantum computing modality. So we have the breakdown and the explanations of that in here. If anyone is interested, let me know. But these are the types of reports that we then produce for vendors, investors, governments, and so forth. That concludes the presentation. The slides that I shared earlier are available on my website. Simply go to andrekoenig.com. You'll find a link at the bottom of it. You can also message me on there if you're interested in any of the charts, and I'll be happy to help.
Thank you very much, Andre. Excellent overview. Any questions? If not, I have a question.
Hey, Andre,
Okay, go ahead. Go ahead, Nick. Yeah, go ahead.
I was just wondering who bought the quantum computer.
I can't tell you, but I'll say this. There is a big pipeline of regional research labs that are looking to buy on-premise quantum computers that don't want to build them themselves or can't build them themselves. You see that in Europe, you see that in Asia. I don't know of any end customer yet. You tell me if you guys have sold any on-premise. I don't think you have, but you know there's no bank or something like that that I'm aware of. But there's at least one European research institute that has bought one, and I know of 2 or 3 others that are on the line to cut a deal by the end of this year.
Interesting. Yeah, it seems like it's something hard to get out of the lab.
Well, you can buy it on IBM.com, but
exactly, you put it on the cloud. You don't need to have it in the lab. I mean, you wanna go maintain that stuff.
not everybody wants to be dependent of an American cloud provider.
Fair enough.
I remember that few years ago, actually NASA bought a D-Wave computer from them.
Yeah.
2000.
Absolutely. D-Wave sold several as far as I know, which is not counted in the data I showed to you. But yeah, no, there is there are research labs that say we want our own on-premise quantum computer, so we can really not sit in a queue, but really also experiment with the technology, upgrade it to our needs over time. And listen, there are folks out there, this is a little bit about geopolitics, that say we don't want to be dependent on the cloud, number one. Number two, we don't want to be dependent on an American vendor or a Chinese vendor or a Russian vendor, whatever it might be, right? Especially if you're a European country, and this could be a transformative technology. So they have different buying behaviors as well. I think ultimately in 10, 15 years, the quantum cloud is what everybody will use, right? In the next few years, I think there will be a big on-premise market.
Yeah. So Andrea, I have a question about. So it's obvious how investors would use this data, right? Like you would look at the trends, you would look at the deals, make judgments, right, and see what other opportunities. If you are a researcher, an engineer, maybe somebody thinking about a startup, all right? So how would you use it from the other side? For instance, let's say you're a young researcher and you decide, should you stay in academia, or should you go to IBM Research, or should you join one of these guys, or should you start your own startup? How would you use it to kind of make judgments and support your intuition?
Yeah, great question. And 2 answers to that. I've been on a lot of meetings and calls and meetups like this, and many times I see engineers, developers using a couple ecosystem slides to frame the discussion of what they are doing. I think that's fantastic. Many are familiar with the quantum computing report. Doug Fink, who's kind of pioneer of that and does amazing work. So I offer an alternative for that, and maybe a little bit more variety. Not trying to compete with Doug too much on that. It's very different. But that would be one aspect, right? And if anybody for their own presentations needs something specific, please reach out to me. The second answer, and I had that conversation a couple of times this week with researchers asking me how they could transition to entrepreneurship. I think there tends to be a lack of really full understanding, or maybe some bias, because there is a lot of hype in some news publications. Somebody who said earlier, I think investments total $2 billion, which unfortunately is not the case yet. So getting a better sense of which type of quantum information science fields, applications, but also regions are maturing faster, sooner, or maybe later. That might be an opportunity as well, right? Depending on your appetite and your skill set. But just getting a better understanding of how users enterprises and investors evaluate quantum, which is very different than a scientist or researcher would evaluate it. I think it's very helpful if you're trying to join a company as an engineer or potentially start your own. So I think it's helpful from that point of view.
Thank you. And one more question. So obviously, all these startups, all of them need engineers. So like in software startups, you have a thriving jobs ecosystem, recruiters, headhunters, right? Like it's a war basically, right? Like if you're a machine learning guy on the market, Uber and Google and Amazon will fight for you, right? Like you basically have to stand up, raise your hand, and the battle will ensue, right? So what is the state of jobs in quantum for the startups? Is there any kind of emerging resource? Because I've seen, for instance, academic consortia just plan to create job boards, and it's like it looks to me surprisingly underdeveloped in terms of jobs and matching candidates to companies.
Absolutely, and I mentioned One Quantum, one of my 3 ventures, which is a community organization. And there we talk every day with dozens and dozens, not every day with dozens and dozens, but we have dozens and dozens startup members. We talk to them every day. We actually just did a survey of what your top priorities are amongst those members. Surprisingly, HR, recruiting, hire only came in number 4 spot. Number 1, surprisingly to me, but made me happy as a business kind of guy, was storytelling, branding, and marketing, which I think 75% of people mention as a priority. Then just sales and obviously fundraising. That said, HR is a big problem. Everybody talks about talent shortage. Almost every day I get an email saying, I have a resume, I have a job opening, do you know somebody? And it's both, right? It's companies looking for the unicorn postdoc that can transition into entrepreneurship and solve some of those problems that Nick presented so nicely. But the business side is getting more prominent as well. More marketing needs to be done. Rigetti launched a new website yesterday, which looks fantastic. Check it out if you haven't done so. But enterprise sales, right? Just enterprise marketing, which are things that we business folks have studied since the days of Oracle 34 years ago. How do you sell something to a JP Morgan? How do you market something to a Siemens? All those kind of things. So those profiles are being looked for more, and obviously there are very few people that have that experience that understand quantum sufficiently, and that's a big gap to fill as well. So if you're a postdoc and looking for something, definitely let us know. There's huge demand for that out there. If you're a business person that wants to get into quantum, there's a huge demand out there for that. Hit up people like Terrell Franz, who is in the audience, to figure out how to educate yourself and become smart. You really need to understand quantum to be able to market and sell it.
Thank you. Thank you. Any other questions? Well, if not, let's thank Andrei again. Excellent talk. Really appreciate it. I guess we all learned a lot from this, and also there's this fantastic data resource which we can peruse. Any appetite for lightning talks? I know it's been a long set today. So does anybody want to present? And if so, we can kind of decide.
I can do it if you're not too tired. And I really enjoy Nick's talk. So it really complements and answers some of my questions that I was going to raise.
Thanks. So listen, what would be the topic of your lightning talk?
VQE, are we there yet? So I'll talk about my experience in the CDL. When during one of the weeks we had interesting calculations for VQE. And that's where I start kind of thinking about exactly the problems that Nick was pointing out at some point.
Sounds good. I mean, let's hear it.
Okay. So I will share with you a link that you can post later. This is for from my slide sharing, and I will go now in presentation mode for my Google Slides. So as I mentioned, I had a great time about a month ago at Creative Destruction Labs. And the topic that I'll cover is what is VQE and how can we use it. I know that most people probably are already familiar with that. Let me figure out how do I hide this part. Can you see my slides?
Yeah.
Okay. No, I wasn't showing that. Okay. So what are the problems preventing its utilization today? And then I'll go over a case study, basically using IBM Q through Tequila and Penny Lane. And then I'll just kind of draw my conclusions and answer any questions. Briefly, for those that are really new, VQE is variational quantum eigensolver. It can solve different problems. The whole point is that the Hamiltonian is considered to be some kind of cost function, and the steps in the process is to prepare some quantum state and evaluate the expectation value of this cost function. Usually we talk about this in Hamiltonian, but when we have to talk to people about like traveling salesman problem and around about clicks and other things, we start talking about cost functions, because this is typical for people from economics and combinatorics. Now, when people who would like to hear more about that, you can go to the SlideShare net, and they have a few talks about this. Basically, the idea is once you prepare your state, you can start rotating different parameters in your state. In this case, particularly, it's very simple. It's just rotation around y, and the angle you're rotating there would change the parameters, and this your trail function would evaluate again the expectation value. And in an algorithm, you just go through each of these gates and trying to figure out with the classical algorithm what is the best next step, and then you keep changing it. Now, and after what you shortly see in my calculations at the CDL, I look up at the IBM, and I found that they had this nice kind of graph where they can show that the exact energy and the VQ energy matching. And this is pretty much the same graph that Nick was showing for lithium. And you can see the configurations and the link that people who are interested, then you can actually go study the IBM. And I really love the way the IBM is preparing the tutorials. These are very useful things for people to practically do things. But there is one caveat. I mean, this graph was computed with a simulator. If you wanna actually do actual simulations and do other things, then things would depend on the implementation. Now in this same tutorial, they go through simulating noise. And then now you can see that there's some deviation from what would be the exact value and what you get with the VQE. So you can see that there's about 3–4% difference. And this is something to be expected with the noisy qubits that we have nowadays. And I'm reminding you about the slide from Nick showing that if you do the calculations, you don't get this nice curve on actual qubits. and then you have to implement some kind of other methods where you do calculation and extrapolations. So the same thing that I mentioned that I was doing at the CDL, and this is the GitHub page where you can access actually our work. And for this week, this was week 2 of the quantum bootcamp. My team, and of course there were other things. It wasn't only these things, but overall the work that we presented to the rest of the people in the bootcamp got the winning cohort project. There you can see actually classical solutions of the same question, the lithium hydrogen using Hartree-Fock, then confined configuration mixing and so on. Now the Hartree-Fock, you can see that's actually off the actual full configuration mixing solutions. But it's important to always compare to see where it should be. If you actually use the tools that we were playing with, you can create a variational circuit, and this is just a snapshot of the variational circuit at one point, and what are the wave functions for one particular run. And these are, again, I'm kind of pricing IBM because these are really useful things when you go to the Q experience and being able to see, okay, what was the circuit that was executed and what was the outcome of the shots there. Now, what started as kind of exploratory project there, well, I was shocked that when I submitted jobs to the IBM Q, we actually had to do hydrogen because for the lithium, I think the 16 qubit was taken by some commercial run, so we couldn't run. We waited for a few days, but we couldn't complete these runs, and we decided, okay, let's go and do a hydrogen because that was the next one we could do. And then I noticed the same thing that Nick was pointing out, that you actually get quite far from where you should be. And there are different methods actually. Now, the blue dot is where you start your algorithm to approach to the value that you would like to do. And there are different approaches like unitary quantum coupled cluster method, or coupled cluster method, quantum cluster method, or you can just submit the job to the IBM. So it seems to be far away from where you want to land. And again, here's some of the links. What we actually learned was, I mean, this was used with the Killer package. And we found that definitely they had a problem with their Breivik-Kitaev implementation. So eventually we had to do the Jordan-Wigner. And once we identified that there was an issue, we thought, well, maybe the Killer just screwed it up. And we look at the penny lane, and we did a little bit different. We kind of randomly, we knew what should be the value, and then we submit to penny lane. Actually, we submit first to IBM with the Killer, then we submit with the same parameters to penny lane, and then we go back and submit again to IBM. And you see that you are all over the map. This is not controlled like what Nick was doing. We have a parameter to access. We just wanted to confirm that definitely these functions within the Killer and penny lane, they were not set up already to take into account the noise and the calibration. So I was thinking, well, maybe if we look at the calibration, we can fix it. But I understood from Nick that calibration wouldn't help you much. So in conclusion, I would like to point out that, well, one has to cross-check the results and then cross-check again. And hopefully, I mean, if we use the proper error mitigation and extrapolation, eventually we will get good algorithms to utilize what is currently available as quantum devices. So with this, I'll stop here and get any questions from you. Again, here's the GitHub you can access. That's the original CDL Quantum. And then if you want a little bit more on VQE or other talks that I've given, then you can access them through the slide share. With this, let me see if there are any questions, or probably if you said, then I'll hear it.
Thank you, Veslan. That was a great lightning talk and an example of what it should be, you know, very concise, very clear, to the point, and of the GitHub link. Fantastic. Thank you. Yeah. Any questions?
Hey, I'd just like to say that was a really great talk, and like you really touched upon how a lot of decisions that you make in these applications, really matter. So I think I just presented like a handful, and you really kind of rounded out a lot of the rest of the choices that you need to make. And so one of these things we've realized for researchers in the field is that a lot of people need to learn, even if you've you kind of know how quantum computing works, there's a lot of choices that are out there. There's a lot of ways you can map your circuits to the qubits. There's a lot of choose your optimizer, choose your ansatz, choose all these kinds of things, and so there's a lot out there to consider.
Yeah, I agree. And that's a lot of fun when if you're doing it right. So I will stop sharing my screen. Yeah.
Thank you very much. Any other questions? Well, if not, I think we just concluded our third quantum conversations. Thank you so much, guys, for all the participation. I think it was a smaller group, but I feel like it was a really more intimate and kind of more communal. We really got through, more interesting set of introductions and learn more about everybody. So I really appreciate your participation. The video will be, as usual, on function.tv, and we'll continue this cadence. We'll probably shift it a little bit earlier. So it used to be the last Wednesday of the month. Probably we'll move it a bit up. So it will be probably penultimate Wednesday of the month. So I'll send the invite as always on the list, and quantum.sv is the resource. So I got the links finally from Alex and Wesley, and I'll share them as well on the site. Thank you very much. And until the next time, see you.
Thank you. Bye.
Thanks, Alexei. Thanks, everyone.
Bye.